Welcome, Professor. Good afternoon.
Hi, Sandeep. Good afternoon. Sandeep, can you give me the access to share the screen?
Yes, I guess you are co-host, Professor. You are co-host, so I think you can share the screen. Bhargav, can you please?
Yes, sir. Now you are able to share the screen.
Right. How was the last session yesterday? Sandeep?
Yes, it was very. Sonal was, we are, performing. We are guiding them till 6:50, and they have submitted assignment also.
Very good.
Yeah. And today we, I have little bit text pre-processing and
Yes.
so before they do parsing, they must know some pre-processing part and stemming,
Yes.
and then they will do parsing. So it's a little bit ambitious exercise, but don't know how much we complete.
Okay, that's fine.
Okay. But we'll give them the code so that they can run together. If they have any doubt, they can ask anytime during the school.
Okay, sure. Okay, all right. Good afternoon, everyone. Hi, can you hear me? Can you see my screen?
Good afternoon, sir.
Good afternoon.
Good afternoon, sir.
So, like I said yesterday, it would be good if you turn on your videos, at least a few of the participants, so that I can. Yeah, thank you. So yesterday it was around 30. Today there are 28 students. Let's hope that the other two will join soon. So welcome to the third day of this winter school, the second day of the NLP talk, and I hope that you had a great time yesterday. You had already gone through you possibly remember some of the stuff that we discussed yesterday, and also I hope that the hands-on experience was pleasant and you got to know about how things work in practice, particularly language modeling and evaluation, etc. So yesterday we were not able to complete language modeling part. We were left with one interesting part, an advanced smoothing technique, right? So today's plan is I'll quickly talk about the smoothing, the advanced smoothing technique, only one technique, only good Turing method. And then I will move to the second part of the lecture, which is the parsing, right? Syntactic parsing of text language in general. Okay. But before starting, so Sandeep, are you recording the video or no? Is it being recorded or you're on mute, Sandeep?
Yes, sir. It is a live YouTube video.
It is live.
We are broadcasting on YouTube live, and the same video can be available from our channel.
Okay, great. Okay, so a quick recap of yesterday's discussion. We discussed what is language model. We saw that language model is basically a way of synthesizing the language, synthesizing text, right? We also discussed a simple method for language modeling, which is called n-gram language modeling. We saw several approximations, several assumptions in n-gram language modeling, for example, bigram, trigram, unigram, etc. We also saw that if we increase n in n-gram language modeling, you'd be able to generate more realistic text, but the problem is that it would overfit, in the sense that the more you increase in n-gram language modeling, you see that same sentence which are present in the training set are being generated in the test set. And we may encounter cases where the count would be 0, right? And therefore we also discussed we need to do some sort of smoothing, right? We discussed add one smoothing or Laplace smoothing, which was just to add a count, add 1 to the count, with the assumption that whatever we assume that we have seen things one more than what we had in reality. And we also we have then discussed that essentially advanced smoothing is nothing but stealing probabilities from probability distribution, existing distribution, where for some bigrams we have sufficient probability, and you steal some probabilities from them and distribute them to the cases where there is no, where there is no probabilities, probability of 0, count of 0. In order to do that, and while we do that, after this we also have seen that the count decreases significantly. For example, if you remember, there was a count of 638, 637. After this discount, it was around 530, 540. So it happened because 99% of entries in that bigram matrix were 0, and you actually had to steal a lot of probabilities from the existing distribution. We also discussed how to evaluate language model, right? We discussed something about perplexity. There are two ways to evaluate language model. One is intrinsic evaluation, other is extrinsic evaluation. In extrinsic evaluation, we take a task or an application, and then we feed the output of the language model to the application and let the application perform, and then we see the performance of the application, and depending upon the performance of the application, we decide which language model is better, right? This is explicit or extrinsic evaluation. Intrinsic evaluation is task independent, and we discuss something called perplexity, which is essentially a normalized version of normalized probability of a particular sentence or a sequence of words, right? We saw that lower the value of perplexity, higher better the performance of the language model, right? We also saw a few interesting smoothing techniques. One was something called stupid back off. So the one was back off, the next one was interpolation, and then there was something called stupid back off, where we if we see that there is the count of the trigram, say for example you assume a trigram language model, 3-gram language model, if you see that there is the count of trigram language model is 0, then you back off and you move to the bigram. When you see that the bigram is 0, you move to the unigram and so on, right? So now these techniques are useful for certain tasks in NLP, for example, text classification, sentiment analysis, etc. But for language model, we generally use a more sophisticated smoothing technique, right? So one such smoothing technique is called good Turing method. So I'll try to give a very brief overview of what is a good Turing method, how it works. But there is a theoretical understanding behind this smoothing technique. I will not cover the theoretical part, but I will give you a handful of ideas about what is this technique. So, but before that, a quick recap of this Laplace smoothing. We have already discussed this one. You see, you add 1 to the denominator to the numerator and add v. V is the size of the vocab. size of the vocabulary to the denominator, right? And we can rewrite this, right? So this was add one smoothing, right? Similarly, for add k smoothing, you say add k to the numerator and add and then basically you need to add v times k to the denominator, right? Let's try to rewrite this expression, this k times v. Let's assume that this k times v is m. Okay, so therefore k is m by v, right? So we will replace k by m by v, right? M into 1 by v. Okay, now why we are doing, there is a nice interpretation behind this replacement. So now mb is k times v is m, and k is now m into 1 by v. You see that now this add k smoothing, add k bigram smoothing is a function of the vocabulary 1 by v, right? V is the size of the vocab, so now it's a function of vocabulary. We can now, instead of fixing this to 1 by v, what we can do here, again we can use the same idea of this back off, right? So instead of fixing this by 1 by v, we can make it as a variable, we can make it a probability by replacing this by p of wi. What is p of wi? P of wi is the probability of the unigram, right? So 1 by v is constant. So what I'm saying is that instead of adding constant for all the bigrams, right? Now this 1 by v is fixed. 1 by v is fixed for all wi minus 1, right? Instead of doing that, what we can do, we can make it context dependent, we can make it bigram dependent, and we can say that this now, instead of using 1 by v, I'm using the probability of wi. Now think about it, this add k is no longer add k. This is now a function of wi itself. It means that probability of, say, m given I is now a function of probability of m. Earlier, it was just a function of 1 by v. So now if you change the bigram, say m given boy given a, right? It is a function of p of boy, right? So the probability of this bigram is now a function of the unigram. Earlier it was fixed. Earlier the amount that we are adding to the numerator was fixed. That was 1 by v. Now we are saying that instead of making this constant, we make it a variable and we make it dependent on the unigram. Okay, this is also kind of a back off, because in order to compute the bigram probability, we are considering the probability of the unigram, right? This is kind of a back off. So this is another way of thinking about this smoothing, and this is called unigram prior smoothing. Why this is unigram prior smoothing? Because we are considering a prior probability of the unigram, right? So now coming to this good Turing method. So the idea again is same, but slightly different from the advanced smoothing. So here the idea is, so use the count when we see that the count is 0. So use the count of things we have seen once. This is very important. Use the count of things we have seen once to help estimate the count of things we have never seen. Okay. Earlier, what we were thinking, what we are doing, we are adding 1 to everyone. Right now we are saying that in order to decide the probability of those counts which is 0, we will leverage the count of 1. In order to estimate the count of 1, we leverage the count of 2. In order to estimate the count of 3, we leverage the count of 4, right? And so on and so forth. Let's discuss an example. Okay, so let's assume, let's define a kind of weird variable called NC. Okay, what is this NC? NC is frequency of frequency C. Okay, what does it mean? Frequency of frequency C. Let's assume that these are some frequencies: 1, 2, 1, 5, 3. Say frequency of the word I is 1, frequency of the word M is 2, frequency of the word A is 1, and so on and so forth. Frequency means count. Okay. Now, what is N1? N1 means how many times in this set, in this sequence, how many times 1 appears? How many times? 2. So frequency of frequency C, frequency of frequency 1, right? N1. What is N2? N2 is frequency of 2, right? Which is 1, right? So let's take an example. Say, right? Say this is the sentence: Sam, I am Sam, I do not eat. Okay, this is the sentence, and let's see the frequency of each of these types. Okay, I appears 3 times, Sam 2 times, am 2 times, do 1, not 1, eat 1. Okay, now what is N1? N1 is 3. Okay, what is N2? N2 is 2, right? N2 is 2. What is N3? N3 is 1, right? Clear? Frequency of frequency C. Now we use this notion to derive good tuning smoothing technique. Okay. So again, let's take a funny example. Okay. So say assume that you are fishing and you have caught these fishes. How many of you are fish lovers? Any Bengali audience? So have you heard of this fish ever? Whitefish, perch, trout, salmon. I don't know. I don't have any idea. So assume that you are fishing and you have caught these fishes: 10 crab, 3 perch, 2 whitefish, 1 trout, 1 salmon, and 1 eel. Okay. I know salmon. I took salmon when I was in USA. So assume that you caught 8 fishes, right? So if you are asked that what is the how likely is the next species that you are going to catch is trout. Okay, what do you think? What's the probability? So these fishes you have already caught. What is the probability that the next fish is going to be trout? Simple.
1 upon 18.
1 upon 18. 1 upon 18, right? Now, if the question is, what is the probability that the next species is catfish? Catfish has not been encountered before, right? So it should be 0. It should be 0, right? So now we are saying that now here good Turing assumption comes, right? What we say is that we estimate this kind of probabilities, which is 0, right, by the count. Can you please unmute your the mic? Someone's mic is mute. Someone still unmute. So now the idea is that we are going to compute the probability of those cases which have not been encountered before by the probability of those cases which have been encountered one time. Okay. So let's use our estimate of things we saw once to estimate the new things. This is the idea being good Turing, right? I already mentioned, right? So, so since the count of catfish or bass is 0, now we look at count of N1, right? What is N1? N1 is 3. 1, 2, 3, right? So then we estimate this by saying that the probability that the next fish is going to be catfish is 3 by 18, N1 by N, right? Then once we get this, if I ask the same question again, what is the probability that the next species is trout? It would no longer be 1 by 18. Earlier it was 1 by 18. It would no longer be 1 by 18. Why? Because we have already stolen some probability from trout, right? So it should be less than 1 by 18, right? Now, what would be the actual estimate? What will be the actual value? We'll discuss. Okay, it must be less than 1 by 18 because we have already stolen some probability and given this probability to new species. So it should be now less than 1 by 18. Now, how to estimate the new probability? So now this is the idea. So P star GT means good Turing. So the probability, the smooth probability using good Turing calculation, things with 0 frequency, it N1 by N. You have already seen, right? Now for unseen like bass or catfish, the C equals to 0. So ML is maximum likelihood estimate. What is maximum likelihood estimate? I hope you have already heard of this term earlier. Maximum likelihood estimate. What is maximum likelihood estimate? Maximum likelihood estimate basically indicates what's the maximum possibility of a particular things encountered encountered in the past. For example, if someone says that what is the maximum likelihood of the word I, you just say that it is count of I by N. Okay, so maximum likelihood estimate of this bass or catfish is 0 by 18 because it has not been encountered before. Now, what is good Turing smooth estimate? It is N1 by N, which is 3 by 18, right? Now next, when we re-estimate those cases which has been encountered right, seen once like trot, how do we recalculate this probability? Okay, so C equals to 1, P equals to, before smoothing maximum likelihood estimate is 1 by 18, right? Now with smoothing C star would be calculated using this formula, right? What is C plus 1? C equals to 1. So 1 plus 1 times N C plus 1 N2 by N1, right? So 2 times N2 by N1. What is N2? N2 is frequency of 2, right? So if you remember, frequency of 2 was 1, right? So this is going to be, sorry, this is 1, right? This is 1. So 2 times 1, what is N1? N1 is 3.
3.
Right? So 2 by 3. Now your new C star is 2 by 3. Okay. Now this is C star, this is count. This is not the probability. Okay. So 2 by 3, right? Now your probability is 2 by 3 by 18. 18 is the number, total number. Now this is 1 by 27. Think about it. Earlier it was 1 by 18. Now it is 1 by 27. So it has got reduced, right? Similarly, we do it for N2. Similarly, we do it for C equals to 2, C equals to 3, and C equals to 4, and so on. Okay. This is the idea. If you do that, now this is the table. This is a table. The number is drawn from this corpus. 22 million words of this news article, and this was the actual count, right? C equals to 0, C equals to 1, C equals to 0. Good Turing sister is this one. C equals to 1. Good Turing sister is this one. Now think about the reduction from 0 to this, 1 to this, from 0, those which has not been encountered before for those entities. Now the count is slightly non-zero number, some non-zero number. For those which has occurred before one time, now this is 0.446, right? For those which has occurred 2 times, now this is 1.26. You see, for all the cases, for all these cases, the number has reduced, modified number has reduced, and all these numbers have actually moved to this case because here the number has increased. Right? This is the original count, and this is the good Turing smooth count C star. Okay. In this case, C was 1, but C star was 2 by 3 reduced. But here C was 0, C star was whatever. I mean, C star doesn't matter because we are essentially counting the probability, but it should be greater than 0. Okay. So for all the cases, you see that the number has decreased because obviously you are taking some probabilities from existing one, you are giving it to 0. So this is the formula. Okay. So we are done with this. Now let us move to today's discussion. Any query? Any query? This would take another 2 hours.
Sir, there was 2 advanced smoothing now.
Yeah,
One
so I'm
was
skipping the
good
second one.
turning in.
I'm skipping the second one.
Okay, sir.
Sir,
Hmm.
in yesterday's lecture, we have seen that we have done +1 directly. So instead of that, now we are doing this, no? Step of smoothing.
Exactly.
Thank you.
Exactly. Okay, so this would take around 2 hours. Okay, so I will take break after 1 hour, and would take questions. So we are done with language model. Now in NLP, if you look at the components of NLP, there are majorly 4 components. I'm not sure whether this has been discussed in the Winter School, introduction of Winter School, but so this is the first slide of any NLP course. Okay. So when we talk about NLP, we generally undergo these 4 steps. One is called morphology. First is called morphology. Second is syntax. Third is semantics, and fourth is pragmatics. Okay. What is morphology? Morphology is the study of words, how a particular word is formed. Okay. What are the prefix, suffix of a word? What is the root of a word, the stem of a word, right? How words are related, how different words in a language are related, and so on. Essentially, how a particular word is created. It is morphology is about words. Okay. What is syntax? Syntax is about how these words are combined to form a sentence, right? We talk about grammars. Okay. So when we say syntax, we do not care about the meaning of the sentence. It may happen that a sentence is grammatically correct, but it doesn't have any meaning, right? So when we talk about syntax, we do not care about meaning. We just look at how the sentence is constructed by combining words in a systematic way, following a particular grammar. Okay. The third step is semantics. When we say semantics, we look at the meaning of a particular sentence, whether it is a meaningful sentence or not, right? It may happen the sentence is grammatically correct, but the sentence doesn't have any meaning, right? In that case, that sentence will not pass the third stage, right? So you talk about semantics, we see that what different thesaurus, different resources like WordNet, VerbNet, Sentinet, different external thesaurus are used to understand the meaning of a sentence. And the fourth one is pragmatics. Okay, now what is pragmatics? Pragmatics deals with understanding a sentence at a particular context. Okay, for example, if I say that do you know what's the time? Okay, so this is the sentence. Do you know what's the time? So this sentence has multiple interpretation. Okay, if you look at the surface level meaning, it basically you are asking for the time, right? But if you think of if you think from from our mom's point of view, right? Our mom is at the morning she is scolding her son that you know what's the time? It's already 9 a.m. and you're still sleeping, right? So if my mom is saying that what's the time, and if your response is it's 9 a.m., then you'll be scolded. Okay, so this is depending upon the context, a sentence has different types of interpretations. Okay, if I ask that I have never got 5,000 likes of my post. So this is the sentence. I have never got 5,000 likes of my post. Okay, it has two interpretations. One interpretation is that literally in the post that I have written earlier, I have not received 5,000 likes of my post. Second interpretation is that I have recently received 5,000 likes of my post, and that's why I'm surprised. I'm so surprised that I was never expecting that I would get 5,000 likes of my post, right? So this is called pragmatics, understanding the meaning of a sentence or an utterance depending on the context. Okay, so that's the last stage of NLP. So in this lecture, we'll talk about syntax, the second part. So when we say syntax, there are two components. The first component is to understand the part of speech of words in a sentence, POS tagging. Okay, so POS taggers deal with estimating the part of speech of each individual word in a sentence, right? And the second part is that once you identify part of speech of words in a sentence, the second part is how these words with different part of speech are combined, right? And how do we understand the entire grammar? For example, given a sentence, can we understand what is subject, what is predicate? Or can we understand that one verb phrase and one noun phrase are combined to form the sentence, right? A verb phrase is composed of verb and noun, or a noun phrase is composed of noun and other parts of speech, and so on. So once you identify part of speech, the next step is to understand how this part of speech and different words with different part of speech are combined to form the sentence. So I was told that this lecture is going to be only on parsing. Okay, so we assume that in this lecture, we assume that the part of speech tagging has been done, right?
Sir,
Go on.
Actually, we will cover in tutorial part of speech tagging. So I mean that's fine, sir.
Okay, very good.
Okay.
So we assume that the part of speech tagging is done.
Yes. We will cover it in. Yes.
Okay. We are given a sentence and we know the part of speech of individual words in a sentence. Just a funny question. Do you have idea about how many part of speech we generally use in NLP? Anybody has any idea? How many part of speech are there in English language? Noun, pronoun, adjective, verb, adverb, preposition, conjunction, interjection. Sometimes article. 8 or 9, right? 8 or 9, whatever. But in general, So there are different sets of part of speech evolved over time in different research. If you go back to 90s, 99, 95, 96, during that time, we used to use 36 part of speech. After that, when we when this pen-tree-bank corpus and other things were developed, we considered 96 part of speech, right? And now these days we use 146 part of speech. I'm not sure how many tags are important, or how many tags will be taught by Sandeep, but there are around 150 such tags, part of speech tags. You do not need to remember all of them, but those are really fine-grained. So, okay. So now syntax, we assume that part of speech is already given. And what is syntax? Syntax refers to the way words are arranged together. Okay. Why syntax? Why it is important to read or to analyze syntax? Because we are interested in grammar checking, right? In also in dialogue management, in any language generation task, right? In any language generation task, for example, machine translation, summarization, question answering. If you do not know syntax, or if you do not know whether a particular sentence is constructed rightly, you won't be able to generate a meaningful sentence, right? So when we analyze a sentence, we first look at the syntax, the construction of sentence by combining words in a meaningful way. Okay, so this should be taught in a linguistic class, but still you all know that sentences are of generally of multiple types, but 4 different types of sentences we generally deal with in NLP. One is simple declarative sentence, where S is a sentence, okay, and sentence is composed of noun phrase and verb phrase. For example, a plane left, right? Imperative sentence like leave, exclamation symbol, where S, so this is a sentence which is formed of a verb phrase. VP means verb phrase, right? Leave is a verb, and this is also a verb phrase, right? Yes, no type question like did the plane leave, right? Here you see that this is the auxiliary verb, right? And you have noun phrase and verb phrase, okay? And WH type questions, for example, when did the plane leave, right? You have WH noun phrase, and then auxiliary verb, and then noun phrase and verb phrase. Okay, so generally these four types of sentences we deal with in NLP. Now this S to VP, right? This is called rule, production rule. Okay, it means that S is a sentence. S symbolizes sentence, and VP is the verb phrase. Okay, it means S is composed of a verb phrase. Okay, or S derives a verb phrase. I will discuss later. Now, important part is as follows. So, when you talk about parsing or syntax, understanding the syntax of a sentence, there are 2 schools of thought, 2 ways we can analyze the syntax of a sentence, right? One way is called constituency parsing, and other is called dependency parsing. 2 schools of thought. Okay, so two different parts are available in the market. You depending upon the task, again you use you choose parsers accordingly. Now constituency parsing technique results different output. Dependency parsing technique gives different types of outputs. Okay, now what is constituency parsing? So constituency parsing, the idea here is that each sentence is consists of different constituents. Okay, what is constituents? Constituents is basically a phrase or a set of words, right, which act as a unit, right? For example, say John. Let's look at this sentence. John talked to the children about drugs. Okay, to the children is a constituent. This acts as a phrase. This is called prepositional phrase. PP. Okay, this is preparational phrase. About drugs, this is another constituent. John talked, these are different constituents. So constituents are units of a sentence, right, which you cannot break, right? And another way of realizing a constituent is that you can move these constituents here and there freely without changing the meaning of the sentence. For example, if I say that John talked about drugs to the children, it is still a meaningful sentence, same meaning, right? So what we did, you moved the entire phrase, the entire constituent here, but the meaning doesn't change, right? But you cannot break a constituent. For example, if I say that John talked drugs to the children about, you move drugged here, you move the word drugs here, right? This is not a meaningful sentence. Even if it is meaningful, it is the meaning is not same as the original, right? So in constituency parsing, the idea is that a sentence is constructed by combining different constituents, and constituents are units. Each constituent indicates a unit of a sentence, right? So now what is the output of, in fact what you can do to test whether this is a constituent or not, you sometimes replace one constituent by a similar type of constituent, right? For example, if let's assume that this is a sentence, I sat on the box, okay, my claim is on the box is a constituent, it indicates some place, right? Now if I replace on the box by there, it's still a meaningful sentence, right? There, right on the box, these are kind of synonymous or similar phrases, right? So if you replace a constituent, you can if you substitute the constituent by a similar type of constituent, the meaning will still hold. Okay, so these are like very vague ways of checking which one is constituent or which one is not, but this is not the actual motivation behind this. So the motivation is that constituency parsing, it says that you give a sentence like this, say Fed raises interest rate. Okay, this is the sentence that you are feeding to the constituency parsing, and you can expect a tree like this as the output of the parsing. Okay, let's understand the tree. Fed raises interest rates. Okay, Fed is a noun. Now this N, V, N.
Like that.
Have any query? Someone's mic is unmute. Any query? So in the constituency parsing, you feed this sentence, Fed raises interest rate, right? And this Fed is noun, raises is verb, interest is noun, rates is noun, right? Now these two nouns are then combined to form a noun phrase, right? This noun phrase is combined with verb to form a verb phrase. Now this noun and verb phrase is then combined to form the sentence. So if you give this sentence as the input, your constituency parsing will generate this kind of tree. Now this kind of tree will essentially tell you about the grammar. It basically says that, from this tree you can derive the rule. So this is say S decomposes into N and V, right? So S implies N and VP, right? So VP implies V NP. NP implies N. Look, NP implies NN, VP implies VNP. these are rules, grammars. Okay. So if you give this as an input, you will get this kind of tree. This is the output of a constituency parsing. And these are constituents, NP, VP, AN, V, these are constituents, individual units. So remember one thing, constituent can also, one constituent can be a part of another constituent. Okay, it's kind of a hierarchy, right? For example, NP constituent is a part of this VP. Right? So the second view of dependence of parsing is called dependency parsing. Okay. So what is dependency parsing? Dependency parsing says that how words are dependent upon each other. Okay. Say this is the sentence. The boy put the tortoise on the rug. Okay. So here the main verb is put. So put, what is the object? What is the subject here? The subject is boy. Right? So let me write. The boy put the tortoise on the rug. As I told, dependency parsing, dependency structure looks at how the words are dependent upon each other, right? So the main verb is put here. The main verb is put here. Okay. What's the subject of this sentence? It is boy, right? So put is dependent on boy. What is the object of this sentence? Tortoise, right? So put is dependent on tortoise, right? The is the modifier of the subject. So, right? The is the determiner, the modifier of the subject. Similarly, here, the is the modifier of tortoise. Right? So, and if I ask, so let us ask 3 questions to the main verb. One is who, what, where. If I ask who, we get boy. If I ask what, we get the object, which is tortoise. If I ask where, we get on. Right? Now, you see the how words are dependent upon, how words are dependent upon each other. Right? So if we run dependency parsing, you get this kind of output. Okay? You get this kind of output. Put is dependent on 3 words: boy, tortoise, and on. What, who, what, and where. Then boy has a determiner, modifier. Tortoise has a modifier. On again has a modifier. On is dependent on rug, and rug is a modifier. Rug has a modifier da. So you get this kind of structure, right? Along with this links, right? Along with these links, you also get the dependency. For example, you also get the label. For example, this is the subject, this is the object, this is the determiner, SUBJ, OBJ, DET, and so on. So you see, there are 2 different ways of looking at a sentence. One way is to look at the constituents and then how these constituents are combined to form a sentence, right? Other ways is to look at a sentence is how words are dependent, and there are different tags. For example, determiner, noun modifier, verb modifier, subject, object, right? Indirect object, direct objects, and so on. There are different tags. Okay. So in this lecture, we'll mostly talk about constituency parsing. Okay. We'll see how we can, what are the ways of getting this constituency parsing, right? A particular way of getting this tree structure, and we'll also see that a sentence can have multiple types, multiple such trees, multiple such syntactic trees. One has to choose one syntactic tree depending upon the rules and grammars. Okay. So any query here? Is the idea clear that there are two thoughts, two ways of looking at sentence?
Yes, sir.
Yes, sir.
Okay. So let's now discuss constituency parsing. Okay. So let me ask one question. Natural language processing, right? Why it is called natural language? What is language? Language is a way of communicating your expression, right? Why it is called natural language? It is dependent for, I mean, it is useful for this discussion. That's what I'm asking. Why this is called natural language?
Because we use it in our daily communication and not something which is artificial or
What is artificial language?
like something which is machine used by the machine.
I can use
It comes. No, you can.
Go on.
Maybe this comes out naturally, like we are fluent with the way we speak, and like we talked yesterday that we not only include English, but sometimes it's a mixture of languages.
So what?
Because it has not been developed purposely. It has been evolved naturally over a period of time.
Very good. It is called natural language because it has evolved over time naturally. I mean, it is called natural language not because humans use this language for communication. I mean, the language of a dog can also be a natural language. We don't know that. Language of monkey can also be a natural language. We don't know that, right? Language evolves over time, and during this evolution of language, we go back and then we invented the grammar. It is not that grammar was invented first and then language came. No, this language evolved and then we went back and then we started understanding why a language looks like this and we developed the grammar. It's not the other way around. But if you look at the language that computer knows or computer understands, right? We first develop the grammar and then we teach this machine to understand the grammar, and then we use the language which follows the grammar. The other way around. Those languages are called artificial languages, right? Now, why I am asking this question here? Because essentially syntax, understanding syntax is nothing but understanding the grammar. Okay, so say you utter a particular sentence. Now, my task would be, or the parser's task would be, to understand that why this sentence has been formed, right? What are the rules behind these sentences, right? So if we go back to 1990s, right, classical NLP era, there were many such grammars, many such rules developed manually to synthesize or to generate sentences. For example, these kind of rules, these are rules, right? Symbolic rules. S to NP, VP, NP to DT, NP is noun phrase, VP verb phrase, S is sentence, DT is determiner. Look at the bracket. This parenthesis indicates that this determiners may be optional, right? You can ignore determiner. NP to NP, NNS. So NNS is again noun phrase singular, NNP plural, and so on, right? As I was mentioning, so these are all part of speech, right? These are parts of speech, and there, as I was mentioning, there are 145 part of speech available, right? VP to VNP, right? These are rules, and using these rules, we try to understand. Oops. happened? Connection got lost from my tab. Give me 1 minute, sorry. So, Sandeep, again, give me the access to share the screen.
Okay. 1 minute, Prof. I guess, sir, you are already co-host, but you again log in. You log out from one ID, sir. Just.
I'm logging in from two of my devices.
So right now you are logging from one device. You are already co-host from one device. Okay, I can see your face. Now you have to log in from your iPad, I suppose.
Yeah, I'm already logged in. I've already logged in and I'm trying to share my screen.
Okay, 1 minute. I will give you 1 minute.
Yes, sir. You can try now.
You can try now.
Yeah. Okay.
Okay. Yes.
So what I was mentioning is that earlier what we used to do, we used to generate some grammars, some rules, and we try to understand the syntax. Okay, syntax of a sentence. Now, the problem here is that this is not scalable as such. For example, let's look at this sentence. Okay, Fed raises interest rate 0.5% in effort to control inflation. This is a sentence. Okay, and if we use a very simple grammar, okay, very simple grammar means say a grammar, say this is a grammar, okay, a grammar containing say 10-15 such rules, okay, 10 such rules. If you use such grammar to understand the to generate the tree, the parse tree, right, there are 592 possible such trees that you can generate from this sentence. What do I mean by different trees, right? Let me again go back. Say, for example, this Fed raises noun interest rate. This is one type of tree, right? And the type of tree can be just again for the sake of discussion. You can say that raises interest rate. Say, this V, N, and N. This can be combined together to form a VP and then S. You just ignore this NP. Can also be possible, right? So there are multiple such valid syntactic trees that can be drawn from a sentence, and rough ballpark estimate says that if we have a grammar with 10 such rules, you can generate 592 such trees out of from this sentence. Okay, and now out of these 592 trees, which one is the correct tree? It's difficult to choose, right? Now what you do in order to reduce the number of trees, what you can do, you can impose more constraint. You can imposing more constraints meaning you are adding more rules to the grammar, right? Say for example, if you impose some constraint, you still see that you can generate 36 such trees from the sentence. Now again, how to choose one tree is really difficult, and most of the trees, I mean, all the trees are like equally useful than other, right? So this is not a very scalable solution. Okay, so what people did in order to tackle this problem is that they started manually annotating corpus. Okay, what do you mean by manually annotating? They took some corpus, some documents, and then manually started drawing the part of speech. Sorry, the syntactic tree, the parse tree for a sentence, right? For example, as you see here, I can't see others. Are you guys there? Okay. So people started annotating parse trees manually. Now think about the effort. Given a sentence, your task is to manually identify this tree. Okay, you are a linguist, you know language well, you also know part of speech, etc. Now you start doing things manually. Now, this is just an example. Say the sentence is move followed a round of similar increase by other leaders against Arizona real estate loans. This is the sentence, okay? And you are manually annotating things. This bracket, this parenthesis notation is nothing but the same tree structure, right? So this tree, this kind of tree can also be written in this way. Fed, noun, verb, raises. This is called parenthesis notation. Noun, interest, right? Noun, rates. Then these two nouns are combined, again another bracket, right? And the parenthesis, then NP, right? Then and the parenthesis VP, another parenthesis S. Okay, so in this way, they started annotating corpus taken from, again, Wall Street Journal news article. Okay, now think about the amount of effort. Okay, so these days you can't imagine, you may not be able to imagine the kind of effort that has been put in early 90s, 2000 by researchers mostly in United States. UPenn, Penn State, Stanford, MIT. So they build a lot of corpus. Okay, a lot of such manually annotated documents, lexicons, thesaurus, etc. Now, once we have this kind of tree annotated manually, right? You know that now you can train your model. Okay. Now you can say that, okay, this is my training set. You train your model. In fact, you can also derive different heuristics. For example, you can see here that how many times say NP derives VNP, right? How many times VP derives V, because you already have these things annotated, right? Now you can derive these rules. Okay. Not only that, you can also estimate the probability of this rule. You can say that NP, you can say that there are 3 different productions from NP. One is NP to NVP, another is NP to VP. I'm just writing things arbitrarily, okay? Another is NVVP, for example, right? So these are 3 possibilities. These are 3 possibilities from NP, and this probability is 0.7, this probability is 0.2, and this probability is 0.1. You can estimate this probability because you already have things annotated, right? So now this project is called Penn Tree Bank. This resource is called Penn Tree Bank thesaurus. Okay, this is publicly available. You can go back and check. Penn Tree Bank. This project was initiated in UPenn around 1995-1996, and then it got evolved. Different versions of Penn Tree Bank were developed, right, over times, right. So earlier, Penn Tree Bank was only one corpus, only one such thesaurus which were useful for parsing. Later on, many such tree banks were developed for different purposes, right? If you want to understand classical NLP, you should definitely go back and check this Penn Tree Bank corpus and the kind of effort that has been put in. Okay, now of course the problem in this kind of annotated data set is that it is extremely time consuming, right? It took around 5 to 6 years to develop even a tiny corpus. But the advantage of this annotation is that this kind of annotation is that along with training your model, you can also evaluate a particular output of a parser. Right? Say, for example, you developed your own parser. You got the output of your parser. How do you evaluate the output of the parser? You should have some gold standard, right? Now you can get gold standard from this Pentree and corpus, and you can check the accuracy of your model. You can check the similarity between the ground truth and the output obtained from the model, right? So now, coming to the interesting part. So, so last time I mentioned that given a sentence, you can generate exponential number of trees, right? If you remember, I said that with simple grammar with 10 to 15 production rules, you can get more than 500 such trees, right? If you add more constraint, more production to the grammar, you can reduce the tree size and number of trees, but still you get around 50 to 60 such trees, right? Now I'm giving you some ideas that why it is so. So let's look at this sentence, right? Forget about these arrows, okay? Just focus on this sentence. The board approved its acquisition by Royal Trust Co Limited of Toronto for $27 a share at its monthly meeting. This is the sentence. Please ignore all these arrows and brackets for the time being. Okay, just focus on the sentence. The board approved its acquisition by Royal Trust Co Limited of Toronto for $27 a share at its monthly meeting. Okay, so and assume that you somehow identified the constituents. Okay, one constituent is its acquisition, another constituent is by Royal Trust Co Limited. This is a PP, prepositional phrase, of Toronto, again another PP, for 27 a share, another PP, at its monthly meeting, another PP. Okay, these are prepositional phrases, right? Now let's try to understand how these prepositional phrases are attached to verb or to nouns, right? Now let's look at it. So the board is the noun here, the subject here. Approved is the main verb. Okay, now its acquisition, now tell me whether its acquisition is a PP, a prepositional phrase of the verb or the noun. I mean, if I try to attach its acquisition to the noun or the verb, which one I should choose?
The noun.
Noun.
Why noun?
Noun.
Because
the board acquisition.
The its in that refers to the board.
It's acquisition, I think, verb, because from approved, it's an entire verb phrase.
So its acquisition is a kind of an object, right? It's not a PP, by the way. Okay, so its acquisition is linked to approve. I mean, if I sorry, I'm not using dependency tree, right? Sorry. It would be the other way around, like this. Okay. Now, by Royal Trust Co Limited, this is a PP. Now, by Royal Trust Co Limited, is it linked to acquisition or it is linked to approve?
Linked to approve.
Why? Acquisition by Royal Trust Co Limited. Who is acquiring this? Royal Trust Co Limited.
Board.
So by Royal Trust Co Limited is connected to acquisition. Of Toronto. Of Toronto, is it linked to acquisition, or is it linked to Royal Trust Co Limited, or is it linked to approved?
Royal Trust.
Royal Trust Co Limited, because by Royal Trust Co Limited of Toronto, right? For $27 a share, is it linked to Toronto, or it is linked to Royal Trust Co Limited, or acquisition, or approved?
Acquisition.
Acquisition. Right? Acquisition.
For acquisition.
Right? At its monthly meeting, is it linked to share or Toronto, Royal Trust Co, acquisition, or approved?
Approved.
Approved. Right? So now think about it. So for a human being, it is so difficult to identify which preposition is attached to which constituent of a sentence. Now from from a machine's point of view, think about how difficult it is. Okay, when you have so many constituents and you do not know how things are linked. Okay, so now the kind of links that we have drawn, this is a valid link, right? Valid link in the sense like semantics wise is a valid link. Okay, but syntactically there can be other types of links. For example, someone can say that say a share, someone can say that, okay, at its monthly meeting is related to this, without knowing the meaning. Think about a computer. Computer doesn't know the meaning, right? It just follows a set of rules. And if the rule satisfies, then you can link this phrase to this phrase to this, or this phrase to this, if the rules satisfy, right? So what I mean to say is that from a sentence, for a given sentence, you can have different such attachments. In fact, the number of attachments is exponential. Okay, let's take another example. John wrote the book with a pen in the room. Okay, in the room is one constituent, with a pen is one constituent, the book is one constituent. Okay, you can say that. So look at the bracket, look at this bracket, right? First sentence, the book with a pen in the room. These are three independent constituents, and as if they are directly linked to wrote. Look at the second example. John wrote the book with a pen in the room. Here you say that with a pen is linked to the book, right? Therefore these two things are within bracket, and in the room is again independent. One can also say that no, this is not correct, this is correct. John wrote a book, John wrote the book with a pen in the room. With a pen in the room are connected, and then the book is independent, right? So from this very simple sentence, you can have 1, 2, 3, 4, 5 possibilities. Okay. Okay. So there are 3 constituents, and you see that there are 5 possibilities. And this is a rough number, rough estimate that people have already calculated. With 3 constituents, you get 5 such trees. With 4 constituents, you can get 14 such trees. With 5 constituents, you can get 42 such trees. Right? Now think how with the increase of constituents, the number of trees is increasing. Right? In fact, there is a simple formula called Catalan number, Cn, which is, this is the formula. Okay, where n is the number of constituents. If you fit the number of constituents here, you roughly get the number of trees that you can generate. Okay, so in a nutshell, what I meant to say is that given a particular grammar, there are multiple ways of generating trees, right? And there is no reason that one can prefer one tree upon another. Okay, so in that case, how do we know that which one is correct, or what would be the correct output that one should choose. Okay, so why this is happening? If you think about the problems, why this exponential number of trees are generated, okay, you see that many phrases, many not phrases, many constituents, many upper level constituents, high level constituents are being repeated in different trees. For example, again, this is another example. Cats scratch people with cats with claws. This is a sentence. Okay, you see that this is a simple example. You see there are 5 different trees that one can generate. Okay, and if you look at it carefully, things are being repeated multiple times. Look at this one, this tree and this tree. This verb phrase is repeated here, same verb phrase. Okay, this prepositional phrase is repeated in this tree, same PP. Okay, this prepositional phrase is repeated here. This PP is repeated here. This blue NP is repeated here. So essentially, same things are being repeated multiple times in different trees, and that is the reason that we are getting exponential number of trees, right? So one possibility is that you can recompute things and you can use them again and again in generating different trees. Okay. So the second problem is ambiguity. And NLP is full of ambiguity, as you know, right? If I say that if I say that, say Rohit Sharma is on fire. Okay, Rohit Sharma is on fire. What does it mean? Is he standing on a fire? No, right? Yeah, so NLP is full of ambiguity, and this is the reason we are interested in solving problems here. So the second problem here is ambiguous parts, ambiguous trees. For example, let's take this sentence. Papa ate the caviar with a spoon, right? So this is one tree. This is given this grammar, you can generate this tree. You can again generate the same tree. You can generate a different tree with the same grammar. Okay, look at these two grammars right here. This NP is same as this NP. This PP is same as this PP, right? But then NP and PP are combined to form NP here, but here it is not. Okay. So here V is directly combined to VP. V is directly combined to NP to form VP, but here V is combined to NP to form VP. Okay. So now from these from these two trees, how do you determine which tree we need to choose? Any idea? How do you determine which one is accurate? Anybody wants to try?
For each of the rules, we can assign a probability like based upon the grammar.
Yeah.
And then figure out which past tree might be more possible.
Yeah. So we are going to discuss something called CKY algorithm. Okay, CKY algorithm is an algorithm which efficiently computes the most probable parse tree for a given sentence. Okay. Before that, a very quick overview of grammar. Right. I'm not going to the discussion of why this is called context free So those who have taken the course called TOC or Automata Theory, right? Theory of computation. Those have some ideas about context-free grammar, context-sensitive grammar, regular grammar, right? I'm not going into the details of that, but the kind of grammar that we generally use is called context-free grammar, okay? And context-free grammar is, I'm coming to the formal definition of what is context-free grammar, but is basically is a set of rules. This is called production rules, right? S is sentence. S derives VP, NP, VP derives VNP, VP derives VNP, PP, and so on. Production rules, and then you have, so this is also production rules. These are also production rules, but these are called lexicons. Why these are called lexicons? Because if you see here, all this part of speech, right, are basically generating surface words. But here, if you look at these rules, they are not generating surface words. Okay. In formal language, this is called these are called terminals, and these are called non-terminals. These are called non-terminals. Okay, I'll come to this discussion. So, so context-free grammar consists of a set of rules, right? And using this grammar, you can get the tree, right? For example, if the sentence is people fish tank, right? People fish tank, right? How do we get the tree? You know that people is generated from N. So this is N. You know fish is generated from N, because this is already given to you. Tank is again N, right? And then what? Then you can possibly use N to NP, right? This rule. Sorry, NP to N, right? And then what? Let me see. If I'm just putting things randomly.
Then NP to NP, sir.
NP to
NP.
NP to NP, and then NPN. So ultimately, our task is to get S. Oh, sorry. This is V. This is V.
Yes.
Sorry, people fish tank. Fish is a verb here. Okay, this is verb. So NVN. Now what? Now this is
NP, sir.
NP.
And then VNP to VP.
VP. NP, VP.
NP to S.
NP, VP to
VP to S.
S.
This is one way of constructing things. Unfortunately, you can also parse a sentence like people. This is not a valid sentence, but still you get a valid tree. Or you can still get a valid tree with a sentence like fish. Right? As I was mentioning, syntax is not about semantics. It is just a structure of a sentence. Right? We do not care about whether the sentence is a meaningful sentence or not. Now, this is the formal definition of context-free grammar. Okay. So, context-free grammar consists of this four tuple: T, N, S, and R. What is T? T is the terminal symbol. Okay. These are terminal symbols. Okay. N is a non-terminal symbol. These are non-terminal symbols. Terminal means the end of the tree, right? Because therefore this is called terminal symbols, which cannot be unfolded further, cannot be broken further, right? S is the start symbol, which in our case stands for sentence, and then R is a set of rules. Okay, R is a set of rules of the form X to gamma. What is X? X is a non-terminal. X belongs to N. And what is gamma? Gamma belongs to N union T star. What does it mean? I'm talking in terms of, I'm talking in terms of a formal language terminology. It basically says that any combination of terminals and non-terminals. It can also be null.
Terminals and non-terminals.
Okay. And using this grammar, you can generate a language L, right? And what is language in our case? This is language. People fish tank. Okay. Sometimes you also have now this is grammar. This is lexicon, as I was mentioning. Production rule. So these are all production rules. Rules can be of different types. For example, a non-terminal can produce another non-terminal, right? This is called unary rule. Okay, a non-terminal can produce null. E is null, right? What is null? Null. So these kind of production rules are very dangerous because it is useful sometimes. It is also dangerous sometimes because using this kind of these are called empty rules. Using this empty rule, you would be able to generate syntactic a parse tree of a grammatically incorrect sentence. Okay, so we generally avoid this kind of empty rule. So this is unary production. These are binary productions because a non-terminal generates two non-terminals. Okay, it's called binary productions, ternary productions, and so on. Okay, rough idea why this is called context-free grammar. Any idea, guys, why this is called context-free grammars? CS students, CS IT students should be able to answer.
There is no rules as such for the context which we are considering. That any
what is context?
That means whatever the right hand of the rule is, there is no such restriction to any.
The voice is not coming properly. The voice is breaking.
Sir, suppose say I'm taking any of these rules and I want to replace it by the right hand side. It does not depend what strings precede or follow it afterwards.
Come again. Sorry.
Suppose say I'm taking the rule VP being VNP, sir. In my actual grammar, when I'm going to be replacing this VP instead of V and NP, it doesn't depend what precedes VP or what follows VP afterwards.
Very good. Absolutely correct. So if a rule looks like this, for example, if the rule looks like fish, VP, rods implies V, NP, for example, it means that you can replace VP by, or say, fish, rods, doesn't matter. You can replace VP by VNP if and only if VP follows fish and VP is before rods. These are the contexts of VP, right? But if you look at all these rules, there is no context in the left side. So independent of whether VP is preceded by something or followed by something, you can replace VP by VNP blindly. Okay, this is called context-free grammar. So now one step ahead, we talk about context-free, probabilistic context-free grammar, PCFG. Okay, and the idea is very simple. Same, we have same set of tuples. Okay, but here each rule, each production rule is now associated with a probability. We say that NP generates NNP, for example, with a probability 0.7. Okay, and how do we get this probability? We have already discussed. We have, say, a corpus, an annotated corpus like pen tree bank corpus. We have seen how many times NP generates NNP out of all the cases where NP generates something, and then you measure the probability, right? And since this is probability, right, it should follow probability rules. For example, all the productions which starts with NP, okay, the sum of the probability should be 1. Very obvious, right? Let's look at example. Here there are 3 such productions which start from NP. Okay, NP, 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 PP, NP, N, and look at the probability 0.1, 0.2, 0.7, sum up to 1. Similarly, VP, there are 2 productions, sum up to 1, and so on. Right? So, so each rule is now associated with a probability. Now, given this kind of PCFG, probabilistic context-free grammar, how do we compute the probability? Remember the discussion that we started with. We wanted to measure, we wanted to disambiguate between trees. There are multiple such trees that can be generated for a particular sentence, and our task was to figure out which tree is more probable, right? So essentially we need to measure the probability of a tree. So how do we measure the probability of a tree? Now, tree is nothing but a set of rules, right? S to VP, NP, VP to VP, NP to NP, VP, etc. Right? So essentially each edge in the tree corresponds to a rule, and each rule is assigned a probability, right? So the probability of the entire tree is nothing but the product of all the probabilities. Okay, we look at all the productions, we look at all the probabilities, we multiply, and that is the probability of the tree, right? So from that you can also go further, and you can measure the probability of a sentence. Now, what do I mean by probability of a sentence? Probability of a sentence, forget about the language model, the way we calculated probability of a sentence yesterday, right? Here, based on the trees, different trees that you are generating for a sentence, we can also measure the probability of a sentence or a set of words or a string. This is nothing but the sum of the probabilities of all the trees. So you have said you have say 500 such probabilities. You just add them, and you get the probability of the sentence or the string or the sequence of words, right? So now again, go back to the sentence. People fish tanks with rods. This is one such tree, and look at these probabilities here with the production, right? So this is one tree, and this is another tree, T1 and T2, right? You see that there's a difference here, right? V is directly attached to VP, right? Where here, this is same. This part is also same, I guess. This is also same, right? This part is also same. This is same, but all V, NP, and PP are directly connected to VP. But here, NP and PP form another NP, and V and NP are connected further to form VP. Okay. So these 2 trees are there, and you can calculate the probability of individual trees, right, by taking the product of all the probabilities. Now for T1, the first tree, this is the probability. For T2, this is the probability. So which one is highly likely? This one is highly likely because the probability is highest for T2. No, sorry. This is highly likely, right? This is highly likely because this is highest, PT1, right? So the first tree will be chosen, not the second tree, because this is 00082, this is 008 and 00024. So this will be chosen. I hope this is clear.
Yes, sir.
Yes, sir.
Okay. Yeah. Now moving to the last part of the discussion, which is an algorithm, and very interesting algorithm to generate syntactic tree of a sentence. Okay. So far, whatever we have discussed, the way we, if you look at the discussion carefully, we have not discussed how to generate the tree, right? We have seen that given a grammar, there are multiple ways of generating the tree, and there are exponential number of trees. You can do all these random attachment here and there, following the rule, right? And you get exponential such trees. And then for each of the trees, you measure the probability and you choose the tree for which the probability is maximum. This is very random, ad hoc, kind of an ad hoc way to choose a tree, right? And this is exponential, complexity wise. Now the CKY algorithm is an algorithm which is polynomial time algorithm. Okay, it is cubic time algorithm. Cubic, it is order of n cube. Earlier it was the algorithm that we discussed, exponential, is a polynomial. So therefore this is more efficient than the previous one. Okay, so again, let us understand what we have. We have probabilistic context-free grammar. We know the rules. We also know the probabilities. Okay, these are the probabilities. And our task is that, given the sentence, fish people, fish tank, our task is to generate this kind of tree. This is the task. Okay. So the CKY algorithm, what we use a kind of a weird data structure, right? Called Parth triangle or chart. Okay. This kind of data structure. It's kind of a half. If you cut a square at the middle, half of a square, you can think of it, right? And task is to get the parse tree of this string, fish people, fish tank, and this cell correspond to fish, this cell correspond to people, this cell correspond to fish, this cell correspond to tank. Now moving towards the top, this cell corresponds to the bigram fish people. This cell corresponds to the bigram people fish. This cell corresponds to the bigram fish tank. Right? We will populate this entries one by one. Moving to the top again, this cell corresponds to fish people fish trigram, and this one people fish tank, and the last one correspond to the entire sequence. Okay. So now the question is, how do we populate these entries in the table? Okay. So we use something called dynamic algorithm. CS folks, you possibly have ideas what is dynamic algorithm. Generally, what we do in dynamic algorithm is that we solve a particular problem, sub-problem. We reuse the output of the sub-problem to the later part of the sub-problem to solve it, instead of repeating things again and again. Okay. So Now let's assume that this is a partial part of this chart, right? And you have already, and assume that there are only two words, and you have already filled up this entry and this entry. Okay, and here our task is to fill up this entry. Okay, and we are already given the grammar, and these are the probabilities of the production rules. Okay, so and this cell corresponds to the bigram, and the bigram is people fish in this case. Essentially, you are trying to say that how we can combine people and fish together to form a constituent here. Okay, so you know that NP, from the rule that NP and VP can be combined. Look at here, right? NP and VP can be combined with the probability 0.9. So here you write S NP VP, and the probability is 0.35 for this one times 0.06 times 0.9. What are the other possibilities? V and NP can be combined through this rule. So V NP, and the probability is 0.1 times 0.14 times 0.5. Right? What else can be combined? Tell me. What else can be combined? NP and NP can be combined through this rule. NP produces NP, and the value probability is 0.35 times 0.14 times 0.1. These are the possibilities. There can be other possibilities as well, right? Not only that, when we explore these possibilities, you can further use them to get more such productions. For example, since you already got VP, you can use S2 VP here, and the probability of this one would be VP is, say for example, this is some number, so 0.002, right? This is 0.002 times 0.1. So we keep on doing this thing again and again. Now look at here and assume that this is 0.0007, for example, and this is 0.0002. Look at here. We have got VP, we have got NP, we have got two ways to get S, right? But we can safely ignore this one because the probability is less compared to this one. So we remove this one. Okay, so this cell is now composed of this 4, right? We can ignore this one because this is highest. This is higher than this one, and we are getting same production S, right? So we can ignore this one. So this 3 production rules can be now used further later stages to fill up the remaining cells. Is this clear? How to fill up a particular cell based on the child cells?
Sir, one doubt.
Yeah.
Sir, in this cell, of course, people, why NP, V and N? Here, VP, NP, VN. How we choose this?
Sorry. Again, come again.
Sir, in the people first cell, we have written NP, VN and its probabilities.
Yeah.
And above we have written VP, NP, V and N and its probability. So how we choose that? We are going to write NP, V, N here?
Yes. So I will discuss this thing. Okay, just assume that we have already populated this cell. We have also populated this cell. Given these two cells, how do we go further and populate the parent cell? Okay, so I hope you understood how to populate the parent.
Okay, sir. Yes, sir.
Okay, now how to populate this leaf nodes I will discuss. Okay, so so far we used this notation, right? This kind of data structure we have seen. This corresponds to 1 1 2 2 3 3. This is 1 2 2 3. If this is 1, this is 2, this is 3, this is 2 3, this is 1 2, this is 2 3, right? And this is 1 3. There is another way of looking at this data structure, which is like this. This is called Finch post data structure. Okay, same idea, but now we are just shifting words at the middle. Okay, now this cell is not corresponding to people. This corresponds to some empty rule, some empty symbol. Assume that there is some empty symbol here. Empty, empty, empty. So 0 0, this cell corresponds to some empty word. This is again empty word, empty word, empty word. This cell corresponds to people now. This cell corresponds to fish now. This cell corresponds to tank now. This cell corresponds to people fish. This is fish tank, and the top one is people fish tank. Okay. Why we are writing this? Because we are allowing empty words here. Okay, we discussed empty rules. We are allowing empty words here. This is called Finch post notation. Okay, we are going to use this. I mean, the idea was both of them are same, but essentially you are moving things slightly right, and you are allowing empty words. Okay, so this is the algorithm. I'm not going to the algorithm. I'm just giving you an example and working example of the algorithm. So assume that this is your rule. This is your grammar. You know the probabilities, and this is a Finch post notation. Fish, people, fish, tank, as if fish, people, fish, tank. The same thing, the same data structure, but now it is now I'm rotating the data structure slightly 45-degree right, and I'm getting this this way. So this is a good way of visualizing things, right? So this cell corresponds to fish, this cell corresponds to people, this is fish, this is tank. This cell corresponds to fish people, this is people fish, this is fish tank, right? This cell corresponds to remember, this is this one, right? Okay, this is fish people tank, and this corresponds to people fish tank, and this corresponds to the entire fish people fish tank, right? I'm going to populate these cells one by one. This is not Finch post, by the way. This is a normal chart. Okay, clear? I'm going to populate these cells one by one using the rule. So now the question that you are asking, right? Remember again, this is fish, people, fish, tank. So what would be the production rules here? Fish, we see that fish can be generated from N and from V. Okay, so N, V, okay, with the probability 0.2, 0.6, right? Similarly for people, for fish, for tank. Okay, directly from the production rule. Now, since you have already generated V and N here, right, you can further use you can use some unary rule, right? For example, you know that from n you can generate NP, right?
Yes, sir.
So NP to n will be 0.2 times 0.7. You already got B. You can get VP. VP to V
Right.
is 0.6 times 0.1. Right?
Yes.
Similarly, once you get NP and VP, you can also get S to VP, because you can use this rule, right? So this is going to be 0.1 times 0.06, which would be 0.006, right? Same thing you can also apply for other cells. Okay. Now remember one thing: if you generate S in multiple ways, so this is one way. You can also use again, just for the sake of discussion, say assume that you can also get S2 NPVP. You can also get it S2 NPVP, because we know S2 NPVP is there 0.9 times NP is 0.18, 0.14 times 0.06. You can also get this S in this way, right? But which one to choose?
Yes, sir.
The one whose probability is higher. Okay, this probability is high, so we can ignore this one. Okay. So in this way, you populate all the leaf nodes or child nodes. Now moving to the bigram. So these are unigram things. Okay. Now moving to the bigram. So what this cell corresponds to? This cell corresponds to fish people. Right? This is fish people. So what you do now?
Yes,
What you do now? Just focus on this part. Just focus on this part. Again, you try to combine N, right? Say, for example, you can combine NP, right? Using this rule, you can combine NP, VP, right? And you get S, and so on and so forth, right? For this cell, this is people fish. So you combine things from here and here and get this one. This is fish tank. You combine this and this here. Sorry, not this one. This one. Okay. Okay. And you populate this one. Clear? Now moving towards the top. What is this? This is very important. Very important to note. This is a trigram, right? This cell correspond to fish people fish. So what are the different ways to combine it? So there can be two partitions. One is you choose fish cell, and you choose people fish cell. What is people fish cell? Which one is people fish cell? Which one is people fish cell? This one, right? You choose something from here, and you combine it with this, and you get something. Basically, you are partitioning here, fish and people fish. This is one partition. Another partition can be fish people and then fish at here. In that case, fish people is this one. And what is fish? Which one is fish? This one is fish. Right? You can take something from here and take something from here and combine. So when we derive the rule for trigram, you can break bigrams in different positions. Similarly, in order to populate this one, this correspond to what? This correspond to people fish tank. So you can break at people, so people fish tank, or you can break people fish and then tank. Clear?
Yes, sir.
Yes, sir.
Okay. But someone can say that I can also break in 2 points. Fish, people, tank. I can break 2 points at the same time. Fish, people, tank. But we do not have ternary rules. Remember this. All these rules are binary, or unary, right? So ternary rules are not allowed. Therefore, we can't do that, right? So once we populate these two, now the last one is a foreground. Fish, people, fish, tank. Now there are, how many combinations can be there? One is fish, other is people, fish, tank, or fish, people, fish, tank, or fish, people, fish, tank, because all the rules are binary, right? So if we partition here, then we take fish, and which one is people, fish, tank? Which one is people, fish, tank? I guess this one, right? Because this is fish, this is people,
Yes, sir.
this is fish, this is tank. So this is people, fish, tank. You take something from here, take something from here, use the rule and derive. Or if you partition here, you take fish, people. So which one is fish, people? This cell corresponds to fish, people. And what is which one corresponds to fish, tank? This corresponds to fish, tank. Or you can partition here, fish, people, fish. So this one is fish, people, fish, and then tank. This is tank. Multiple ways, right? So we generate rules here, right? So now this is our final rule. Now look at which rule is highly likely out of, there are 3 rules. Which is highly likely? Which one is highly likely? I think this one, right? So therefore we know. Now I actually forgot to mention one thing. When you derive things, when you determine that, say when you determine this NP implies NP and PLE, and assume that you determine this from this, and so say this correspond to 0, 2, right? And say this NP. Let's assume that we also track from where we derive this cell, from where we derive this production. Okay, so because this would help us unfold things. Ultimately our task is to get the tree, right? So if this is the production, if this is the final production, let us understand from where we derive this production. So this NP, we took this NP from here, we took this VP from here. Okay, so S2
hello
NP VP. Okay, and we know that NP came from
यार तन्मयला सांगा ते माझे चालू आहे.
Someone's mic is unmute. Can you please mute it? S2NP VP is the last production. We know that this production was derived from this cell and this cell. Okay, and we also know that this NP is derived from this cell and this cell. So this is NP. This VP is derived from VNP, which is this V and this NP, VNP. And we know that this is NP to N, this is NP to N, this is V to fish, this is NP to N, right? And since we have already got the the last symbols, then you go back to the your lexicons and you try to match it, because you already know the sentence: fish, people, fish, tank. So this fish is N, this fish is in, this people is in, this fish is verb, and this tank is noun. Okay. In this way, you get the highly probable, highly likely tree that you can generate using the grammar and a given sentence. Any doubt? This is polynomial time algorithm, order of n cube. Why this is order of n cube? If you look at the algorithm, it would be easier to explain, but I'm not going into details of this algorithm. It is time consuming. So let's keep this one. Any doubt here? How many students are there? 38. Okay.
Sure. This means algorithm says that we are moving for the last frame. So we are moving and we are choosing the maximum probability.
Yes.
In the combination.
Yeah.
Okay. Thank you.
So when we get the maximum, the highest probable production, we then unfold, we backtrack. This is called backtrack, right? We backtrack and we look at the previous rules from where the subsequent rules are generated, and then we unfold the entire tree.
Yes, sir.
So the last part, there are 2 more slides. Okay, so please hold on. So the important part, as I was mentioning last day, for any NLP model is to evaluate, right? To evaluate things. How do we evaluate a parser? How do we evaluate a parser? So we can evaluate a parser based on some ground truth, right? Some manually tagged parse rule, right? Let's assume that for this sentence, sales executive were examining the figures with great care yesterday. For this sentence, this tree is the this tree is the gold standard tree, manually annotated tree, and this tree is something that you have generated using your model, using your parser. So essentially, we need to see whether, how similar these 2 trees are. Okay. And how do we do that? How do we do that? Very simple idea. So we first mark all these words. Okay, we mark all these words like this. We mark the start and end of every word. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? You mark it. Okay. And then what we do, we try to expand, or we try to derive, we try to represent this tree using parentheses. Okay, how? Say S, this S spans from 0 to 11. Okay, so S 0 to 11. NP spans from 0 to 2. 0 to 2. VP, this VP spans from 2 to 9, right? 2 to 9, right? Then this VP 3 to 9, 3 to 9. So essentially, you are tokenizing this tree, right? You are breaking things into different tokens. Okay, so these are now your tokens. Okay, you do it till this portion, till before non-terminal. Till all the non-terminals. You capture all the non-terminals. You do not capture terminals, right? You just capture all the non-terminals. Similarly, from the output that you obtain from your parts, from your own model, you can again get a bracketed notation, right? And say this is the bracketed representation of this tree. Okay, now you just simply use precision recall. You all know what is precision recall, right? How many of you do not know what is precision recall? What is precision? What is recall? Precision recall. Anybody here who doesn't have any idea about what is precision, what is recall? Okay. So I'm assuming everybody knows. So this is the gold standard bracketed font. This is the output of your model. So now you compare. This is one set, this is another set. You compare how many of them are correct. These two are correct. This is also correct. This is also correct. Okay. So what is precision? Precision is out of all the items that you returned. Okay. How many of them are correct? So how many items you returned? 1, 2, 3, 4, 5, 6, 7. Out of 7, how many are correct? 3. So 3 by 7 is precision. What is recall here? Out of all the correct items, how many of them are correct? How many of them are returned? So these are correct items: 1, 2, 3, 4, 5, 6, 7, 8, and 3 of them are returned. So 3 by 8 is the recall. And we all know what is F1 score, right? Harmonic mean of precision and recall, and F1 score is 40% in this case. But if you look at this thing carefully, right? If you look at these two trees carefully, where are the major differences? Why the accuracy is so less? Why only 40% accuracy? Seems most of them are correctly identified. Only this part has got connected to this NP here. And because of this wrong attachment, this wrong attachment has got propagated to the top, right? Because of the wrong attachment, it affected NP, it affected PP, it affected VP, it also affected VP, also affected S. Okay, so in this way you can evaluate the model, right? Sometimes what people do is that people do not people also measure. So this is called labeled precision. Why labeled precision? Because each of these brackets or parentheses is associated with the label, right? One can also do the same thing by ignoring the labels. So just like this, 0, 11, 0, 2, 2, 9, just to check whether the spans are correctly identified or not. 4, 6, right? Here 0, 11. We do not care whether this is NP, or this is VP. We just care about whether this span is correctly identified or not. This is called unlabeled accuracy. Okay. In that case, you do not consider these labels. Okay. So we are right on time. We are done. If you have any query, please let me know. Any query? Any query? No? Okay, in that case, I'll stop here and I will request Sandeep to start the next session. Okay. And this is the contact. You can reach out to me through my email, tanmoy@iit.ac.in. As Sandeep was also mentioning, I am also active on Twitter. I generally post my research activities on Twitter, so you can follow me, or you can look at the post, right? And most of the stuffs that I do, research or teaching, what I do, are available on this site. I regularly update my sites, and if you are interested, if anybody is interested for internships and all, you look at our site LCS2.IITB .ac.in, right? Just let me. We regularly post job advertisement and etc. So, so here you see our research, right? If you're interested in internship, recently we floated this winter internship. We selected students. This internship will also be available for summer. Around March, April, we'll float the next internship advertisement, paid advertisement. If you want to know about our research, these are the things that we generally do, right? And other events, etc., publications, etc., are all available here. So feel free to browse through our web pages, and feel free to contact me at any point in time if you feel some of them interesting for further discussion. Okay.
Thank
all
you,
right.
Professor.
Thank you very much. I hope you had a good time last 2-3 days, and you will enjoy the remaining part of the winter school. You will get a lot of exciting talks, more sophisticated NLPs, deep learnings, right? And at the end of the winter school, I hope that you'll have decent ideas about things, and that would motivate you guys to start working on NLP. Okay. Thank you very much.
Thank you, Professor.
Thank you, sir.
Thank you, sir.
And one way, sir, I always advise students to connect. Twitter is the best way to connect with the researchers working in the area of NLP, something like. So I actually in my PhD, I gain a lot in using Twitter. So some of the best people like Jan LeCun, so they frequently post new things about any libraries or new papers. So that was the purpose. So I asked student to follow you and some other professors on Twitter.
Sure,
So that's
sure.
the only idea.
Sure.
Thank you, Professor.
Thank you. Bye.
Now,
have a nice day.
Okay, thank you. And we'll take 10 minutes break right now, 5:11. So let's meet at 5:25 and we'll start the lab session. Okay. Thank you. So we all are joining around 5:25. Thank you.
Hello, good afternoon. Am I audible?
Yes, sir.
Afternoon,
Audible.
sir. Yes, sir.
Audible.
Can you see my screen? Hello.
Yes, sir.
Yes, sir.
Thank you. So, welcome to this, laboratory session on, parsing. Now, before we get into the parsing, I guess there are 40 students and you know something about some preliminaries. So this is today's lab plan. Okay. So first thing is I guess all of you have downloaded the assignment, because the assignment contains what we are supposed to going to do. So this is basically get introduced with the two library, NLTK and SPACY. Then text pre-processing. So here we are going to learn regular expression, tokenization, stemming, lemmatizations, and stop words, something like. Then we will go to the part of speech tagging. Then use POS tagging, not implement, but POS tagging in NLTK and SPACY. We'll talk about brown corpus and pantry bank, dependency parsing, chunking, context-free grammar in NLTK, probabilistic context-free grammar NLTK, and CKY algorithm in NLTK. Okay, so this is the today's plan to cover in in the next 1.5 hours. This looks very ambitious, but let's see how much we can finish. Okay, and but I have provided you the Jupyter notebook, so you can you have to just run the code. Now this is the assignment that you are going to do. The assignment is basically on tweet cleaning part, pre-processing part. So you all people are supposed to get the data set from here website, HESOC dataset, which is a head speech dataset. Now you have to get the text and you have to do the text pre-processing. So you have to write the script. Now I will tell you how to write script, everything. Okay, so now this is today's task. Okay, so with this, let's start with Google Colab. So in Colab, basically now I spent 6 to 7 years in NLP field. So my suggestion is that get the read of Windows from your laptop and install Ubuntu. First thing is, if you want to be a really good NLP programmer or something, like if you want to do really get a great job, programming, then Windows, even in my laptop contains Windows, but I'm just telling you that I have dual operating system. So get the dual operating system, gets the Linux or Ubuntu version, and try to learn Google Drive. Okay, sorry, Colab. So basically in Colab, I will just give you some 1 minute quick introduction. Now here we are using the IPython. IPython stands for interactive Python. Whatever you are doing, that is a Python. Now here there is a cell and you can just write script code, something like that. So first thing is, if you open any Colab, then there are two kind of shell. This is a code shell, and I can add the text cell also. So here I can write anything like Colab introduction, something like that. Okay, so this is my some comment or something like. So if I want to do bold, then I will write like Colab. Okay, so let's see. I'm just giving you, this is my text cell. Now in code cell, if you write something like, then editing. Okay, and now so here I can write commands and everything, and here I can mount the Google Drive. So whenever I mount the Google Drive, they will ask me the permission, connect to Google Drive. Okay, So mounting the Google Drive so that I can access any file on the Google Colab. Now, one more thing I will tell you that biggest problem whenever I do programming, I don't have a platform. Suppose if I do Java programming, I need Java, then etc. Now here you are in cloud, okay, Google Cloud. Google provide this is a platform as a service. That means you can write the codes over here. You just need an internet connection, no need to install any package and everything. But so this is one advantage. But I recommend you to use Anaconda. You must learn how to create virtual environment. That is not the right now. I'm not going to get into this virtual environment part. So this is the drive. Here the drive are connected. Okay. Now if you go to the drive, the simple command is there, ls something like that. Now you can go to this using some those command. You can go get into this. You can get some ls command, standard command. You can go to the my drive, and here you can access your entire Google Drive. Okay, so your data should be over here, and you can access through Colab. Okay, and you can install any package from Colab, like pip install, pp, something like this is a command to install any package. Okay, if that doesn't have. Now earlier here, Colab provide directly this shortcut, but this was a command to mount the Google Drive earlier. So if you don't find this, you can write this code also. Okay. Now important thing is that Colab provide GPU and TPU. Now if you go to the notebook setting part, fine. Here you can use hardware accelerator, so GPU and TPU. Now in a NLP when you deep learning problem, when I use deep learning techniques in natural language processing, then I need sometimes GPU, because GPU is 100, faster than normal CPU. So I can use GPU or TPU, something like that. Okay, right now it is none. So if you want to check it, okay, save, then just run this command, import torch CUDA is available, something like that. Then you will get whether the GPU is available or not. So it will just taking some time. Okay, so no GPU. Okay, so if you select GPU over here, then entire runtime is restarted, and you can use here edit notebook setting, and you can choose GPU or TPU, whatever you want to choose.
Sir, one question. If
Yes.
we select TPU, the code will run faster as compared to the time we'll select the GPU.
I'll tell you, whenever you do some kind of multiplication, you train the model, then you you have to write some code. If you use PyTorch, you have to do some little bit modification on the code, and that will run 10 times, 15 times, 20 times faster than normal CPU.
Okay, in case of PyTorch
or TensorFlow, when
or
you
Keras, anything.
Yes, Keras, everything. In normal CPU, it will take 20 to 25, but it will run 1 minute, 2 minutes.
So it will run faster than GPU also.
Yes, TPU.
With certain modifications.
Yes. You have to just check. Okay. So you have to little bit change in a code. You have to use code. That part. Okay.
Okay.
So one more thing here. So this you look at C. Now Google never use Windows. You see this all Linux libraries. So as I told you earlier, that use only in your laptop. One must, if you are an NLP programmer, then at this one Windows you can keep, but use Linux as other operating system and do programming in here. Okay. So this is my point actually. Now, if you want to, temporary upload a file, okay, then you can easily do this. Like, let me go through. So you can, temporarily upload any file, PDF or whatever you can say, review. Okay. So this file will get over here. Okay. So this is basically, okay, review. So this file is over here. So you can temporarily upload the file, but please remember here Google give you a runtime, and the review.pdf is it won't be permanent in the runtime, but until the current session is going on, the review file is there. So if you don't want to use Google Drive, then you can use temporary, you can upload the file from here also. Okay, so here is, you can refresh. So this is all about Colab. Fine, here the RAM and disk. And one more thing, Google Colab is in 1 or 2 year. I mean, I guess it's 2 year. Google started to providing Colab as a platform as a services. Now it is trying to make popular. I mean, Google is trying hard to make Colab popular. So right now it is free, so you can use as much as you can. So do programming in your Anaconda notebook, but whenever you want to run, whenever you want to use GPU, then you can use Colab. Okay, freely available GPU. Fine. So with this, I will stop the Colab part, and we'll go to the our part is tokenization part. Okay, so first thing is text pre-processing, tokenization. And there are two libraries, Spacy and NLTK. Now I am focusing that Spacy is good library compared to NLTK. This is my take on. This is, I personally believe. I may be completely wrong. So I will show you. You have to just write import Spacy. I mean, no, in Colab all the packages are installed. So basically these are the command. I mean, you can import the Spacy. You can load the English module, German module. There are many various languages, but I'm loading the English. Okay, so this is creating screen. I mean, there are various shell. Now the cell is going on. Okay, this is another cell, my string. So I can do tokenization over here. Then now just see over here. The Spacy can understand 10 kilometers. I didn't put a space, but it also done 10 and kilometer as a separate token. Okay, and $10.30. So it also can recognize the dollar and 10.30 is a two different token. So this is the advantage of using standard tokenizer. So in NLP project, try to use standard library for tokenization, because tokenization is the first part. Okay, something like that. Fine. Okay. So and this here, if it also consider over here token text, like we are going to. So you cannot put in single unit comma here, so you can write slash. So it also understand we are going to USA. Now USA, there is a punctuation mark, but it consider this is a one token. So this is also a good tokenization technique. And then counting tokens, index positions. Okay, these are some codes, you just check it out. Okay, it's not, I mean, it's very trivial thing. I'm just passing the this is one method. So doc5.2 is a better token. So it index start with 0, then slicing. Here why we are doing slicing. Now you cannot reassign the token like my dinner was horrible and your dinner was delicious. Now here the code is basically you cannot change the token. Okay, so try to change my dinner was horrible, my dinner was delicious. This is not happening. Okay, so you have to change the code. Okay, so this will give you a error. Fine, so this is a type error. And here also you can use named entity. Now you see here the Apple to build Hong Kong factory for 6 million. Now what is name entity? Like ACM is a name entity of type organization. Similarly, if you say my name Sandeep, so I am a person. So person, organizations, money. So these all are basically a named entity. So you can easily extract the name entity. Just write Apple. This is a string. NLP is a Spacy object, and doc8. Okay, so doc8, you just do all tokenization, and doc8.end. This is a command which gives you all name entity. Now see, this is syntax. Actually there is no no such big deal, so I'm moving very fast. Okay, so this is all about, named entity. So there are three named entity: Apple, Hong Kong, and 6 million. Okay, so these are the three named entity. This is a tokenization. Okay. Now tokenization, see here, Hong Kong, there are two different token, but named entity is only once. So the making a name entity. Now those who are doing MTech, PhD, I mean there is a problem. Okay, to make a name entity recognizer for Gujarati, for Marathi language, for Tamil. So these all are open problems. So you can use this, some deep learning models or some, I mean, there are still open research problem. And Gujarati or Marathi or Tamil, these are the low resource language, and nobody will work. We have to work. I mean, since we are the native language speaker, so nobody come from US and that because the person doesn't know the semantics of Tamil or Gujarati. So unless we didn't work, then no, I mean our language will remain always low resource language.
So
Yes.
The spacey dot explain, this function returns the named entity?
Yeah, no.
Or the ENT dot, yeah, the last line, yeah. Can you please explain? Yeah.
Yes. And dot text, it will print Apple. Okay. And dot label, what is a label? That is an organization. Okay. And dot label underscore, this will print company, agency, institution, etc., etc. This is
okay.
So to make a sense that what is organization, so organization means company, agency, and institution. Similarly, Hong Kong, it will, yes.
I wanted to know which exact function was giving me the named entity in the spacey library. Which exact function?
Yes, this en dot text.
ENT function. Okay, this ENT dot text.
ENT dot text will give you a text which represents name entity, and ENT dot label will give the label what kind of name entity.
Okay, so this dot ENTS gives me the entities, and then we'll take a for loop and extract the individual entities.
So it's written the
okay.
object.
Okay. Yeah, I got it. ENTS one. Okay.
So this spacey part, tokenization part is over. So it's very trivial one. So I will move very, very fast. Okay. I mean, because we have to cover a lots and lots things.
Yes, sir. Yes, sir.
So now comes the regular expression. Okay. The regular expression, is again a powerful tool. I mean, Python provides, a very good package for the regular expression. So something like that, text is there. Okay. So you can, so this is pure Python text. We are not using anything. Okay. I'm just trying to run the notebook. So it is taking some time. So array or regex or regular expression is a sequence of character that forms a search pattern. Okay. Regex can be used to check if string contains specified search pattern. Okay. Now let me give you example that in a document, if you want to find particular, let's say phone number, particular email address, if you want to extract, then the best thing is write down the regular expression. Okay. So it will, gives you phone number or email address or something like that. So these are the, pure Python command. Now you can use the RE package in Python. So, pattern is equal to contact. Now you have to, use search method of RE. Take 1 minute, excuse me. So this is basically, a search method, re.search, and it will return a match object. Okay, match.research. So if you type, match, something like, fine, re.match. Okay, so match will give you so many things. Match dot, if you type, you will get a list of all and expand. So position, span, everything start position. Fine. So here we'll try to print the match span. So what it will give you the position of contact from 5 to 12, starting number, ending number. Okay, so match object. Fine. So now, to check the digit, alphanumerical, white space. Now these are the characters. /D means for digit. Okay, and the pattern is like file 25. Then the pattern is something like, okay, we write like this. File, then /D. So it will match the file 25. Then alphanumeric AB1, white space, non-digit, non-alphanumeric, white space. So these all are, one way to find out the patterns. If you want to extract some pattern, then this is the character you can use. Okay, something like, let's say I want to extract this phone number, similar number from my text. Then you can write my telephone number is so and so, and you have to pattern, like this is a pattern, digit, 3 digit and 4 digit. So here is, and here phone is basically match object 23 to 35, and match is so and so. Okay, something like that. Now the quantify. Now here is difficult to write three times. I mean, here I'm writing D at least 10 times. So if you want to write quantifier, then here you can use curly bracket 3, then exactly 3 times, 2 to 4 times, 3 or 0 or more times, once or none. So these are basically character which I can use with this character. Okay, so similar problem. See here, phone is equal to re.search. I can use like re.search D3, D4. So this is again, okay, I can use get similar result like span 25. So what I have used quantifier character. Okay. Similarly, there is the OR operator. If I want to search man or woman, okay, then here is match is man and match is woman. Okay, so this is and. Now start with, end with. Now this character are very critical. Now this power character and dollar character. This character is used to start with, and this is end with. Okay, so end with number and start with number. Fine. So this is all about. Now I have given you this notebook. Okay, so you can upload this notebook and you can practice over here. Any question till now? I mean, this is very trivial one. I mean, just as a formality, I have to teach you. Otherwise, I don't think so.
Yes, sir. We are getting it.
Getting? Okay.
Yes.
Very good. Okay, so let's back to the stemming part. Okay. So regular expression is over. Now let's back to the stemming part. Okay. Now in linguistic morphology and information retrieval, stemming is the process of reflecting in inflected word. Like for example, computer. If I write computer, okay, let's say computer. Okay, now I can write compute also. And I can write. So what is the root word? The root word is, this is the root word. So basically we are chopping off the character either from prefix or from suffix to get and get the word in a root form. Okay, so computer, compute, etc., etc. Fine. Now stemming, spacey does not support stemming, or it only support lemmatization. So for stemming, I have to use NLTK. So please keep this thing in your mind that yes, anyone want to ask questions?
Sir, what is the exact difference between stemming and lemmatization?
Okay, I'll take it. Okay, now let me tell you. Okay, I'll get back to you 1 minute. Just because I have exercise for this. Just 2 minutes. Give me 2 minutes. I will give you a difference between.
Yes, sir. Yes, sir.
Let me tell you. So first understand, when I chop off the character, I get the by chopping off the character, I convert a word into the root word. Okay, so basically reducing inflected word like running to run to their word stem, base or root form. Right? Okay, so we will use Porter stemmer. Now this Porter stemmer, okay, 1 minute. Porter algorithm developed by Martin Porter in 1980s, okay, before our birth, on my birth. The algorithm employs 5 phases of word reduction, each one with a mapping rules, like, some suffix and mapping rule. Now we don't go in detail part because there are many people. Even my supervisor has, long back finished his PhD in the, this stemming, and his paper, yes, I mean, it is worth to look his paper. I will show you at the end of discussion. Let me tell you. Parser. Okay, so this is a yes parser, and I will tell you yes. Okay, 1 minute. So let me show you this paper first. Okay, yet another suffix stripper. Okay, so you can this paper was published in a ACM, I mean TOEIC journal, which one of the top tier journal. So you can read his paper. I mean, it is based upon stemming. Fine. So let's back to our business. Fine. So Porters. Now we will implement the Porter stemmer. So first you have to import NLTK and NLTK stem Porter. Fine. It is taking some time actually. Okay. So this is first cell. Okay. Now my suggestion is whenever you do any project, use interactive Python, IPython. Okay. Rather than so once you are confident, then you can use PyCharm and you can use normal Python. Otherwise, this is much better. Okay, so you will get some understanding. So now I'm creating the object of Porter stemmer. Okay, now let's see. Run, runner, running, run, easily, fairly. Now see, we want to stem this word. Okay. Now this stemmer does not use any external library. Let's see. This is a list object. Now for each word, we will try to convert into the root word. Okay, so just see. Oh, 1 minute. I forgot to run this cell. Okay, so just see run. That means there is no stem or root for run. Runner. Now here runner is noun, not run. Running, run. Ran. Okay, runs, run. Now this is wrong. Easily. Fairly. Okay, so stemmer has some limitation. Now I will discuss how lemmatization will overcome this limitation of stemmer. Fine. Okay, now one of the other popular stemmer is snowball stemmer. Okay, this is this is somewhat misnomer. A snowball stemmer name suggests stemming language developed by Martin Porter. Okay, so this is Porter snowball stemmer. So you just use the English. Okay, now see run. Same example we will try to solve it. Okay, now here see fairly it is able to get the fair. So this is the improvement of on previous Porter stemmer. Then still this makes a mistakes over here. Easily. Okay, and fairly will improve with fair. So little bit some kind of improvement. Runner, running, runs, easily. That is. I mean, you can use this word also, general, generation, generally, something like that. Let's start with this also. I mean, you can use any words. Okay. Now here is some word, consingling. Okay. Now use the Porter stemmer. Same, okay, but use this Porter 2 stemmer, that is snowball stemmer, it will give you better. So whenever you want to use, stemming, this Porter 2 is, snowball is better than this one. So this result suggest. Fine. Now here is a very interesting example. I am meeting him tomorrow at meeting. Okay. So this is very, very critical. I am meeting him tomorrow at the meeting. Now here meeting is a verb and here meeting as a noun. So let's see how, I mean, there is no need to, do the stemming of noun. You can do the stem of verb. Fine. So let's first do the P stemmer. Now see I, am, meeting, meet. Now look at over here. It has also converted meeting into meet. Now this meeting is a noun. This meeting is not the verb. Okay. So that thing you have to see. So here word meeting appear twice. Once as a verb, once as a noun. And stemmer treat both as equally. So these are the problem with stemmer. And we will try to, overcome the limitation of such, stemmer in the next example, that is lemmatization. Okay. Now someone has asked me this reason. In contrast to stemming, okay, lemmatization looks beyond the word reduction. Okay. Now let me tell you what is the root form for is, are. It's a to be. Fine. So spacey doesn't support stemming, but it supports lemmatization. So we will do the lemmatization. Now see here. I saw 18 mice today. Now what is the root? What is the root of this word mice? Fine. Just look at this over here. Okay. So I is a pronoun. So is a verb. Here I have used part of speech, noun, and mice, mouse. Fine. Now this is a lemma number. Okay. So don't worry about, ignore this number right now, and mouse. Now this will not happen in, stemming, but lemmatization. Fine. So the lemmatization is much better than stemming. Okay. Now let's solve this problem. I am meeting him tomorrow at the meeting. See here, this meeting is still there at meeting because this meeting is a noun and this meeting is verb. Okay. So lemmatization is an improvement over, on stemming. And this is another example. That's an enormous automobile. Now that is, so see here, it is converted into B, to B form. Okay. So this is all about lemmatization part. Okay. And stop word. So let's back to the.
Hello,
yes,
sir.
Yes, yes.
Sir, you have used NLTK for stemming and you have used SPACY for lemmatization, right?
Yes, yes.
So these lemmatization facilities are also, libraries are also there in NLTK.
Yeah, his NLTK is there.
Okay.
But what I am telling you that SPACY is much richer library, and this is my experience.
Okay.
And one more thing, when in my PhD, and I have performed a lot of, so many, I spent, maximum time, unnecessary time, unnecessarily busy with, experiment. And I find that, there is no need to do stemming or lemmatization, because in the text classification result, I find better result if I don't do stemming or lemmatization. So this was my experience. Now, I might be completely wrong. Huh?
Okay. It's okay. Thank you, sir.
Okay. So this is basically a stop word. So, NLP default stop words. So these are the stop word under SPACY, out, would. So these are, you can have a list of stop words, and the total number of stop words are 326 are the stop words. Now you know that stop word doesn't make any sense. So if you want to clean the corpus, then generally we remove the stop words. Fine. Now, if you want to check any word is a stop word, then this is a simple command. Okay. Now I can write NLP vocabulary mom is stop. So this is a false and this is true. That means this is a yourself is a stop word and mom is not the stop word. Fine. Now let's say this lol. Okay. Now lol is, people laughter, laugh after loud or something like that. Okay. So this word, if I want to add as a stop word, then I can use NLP.default stop word. Okay. So this is a command to add the stop word. Now you can see it's a true 327. Okay, so it increase. So in some corpus, if you are doing some experiment and you want to add that this word should be in a stop word, then you can append the list. Right. Similarly, you can also exclude word like beyond, okay, from the stop words. Okay. So this is basically length of 326. Okay, so we again came back to 326. Okay, now look at see, is NLP beyond? Oh, it's a true. I don't know what is it. Okay, it's a true. I mean, I have removed it. Okay. Anyway, I will fix this problem. Okay, later on. This should not be happen. Okay, 1 minute. Okay, I'll get back to this. Okay, so stemming. So next is the stemming part. Okay, okay, now stop word is over. Okay, so with this, let's start with the text cleaning part. I want to tell you. So whenever you have given a corpus, the first thing is you have to convert all letters into a lower or uppercase. Generally, we convert text into a lowercase. Then you can remove the numbers. 1 minute. You can remove the punctuation, some accent mark, remove white space, expanding abbreviations, removing stop words. Okay, so these are the steps of text cleaning. Now, in this notebook, I'm going to tell you what are the steps. Okay, for the if you have given the corpus, then how can you convert this corpus into the how can you clean the corpus? So basically the first thing is to convert text into a lower. So you have to just write x.lower. No need to use any library. Simply use this word x.lower. Okay, so everything gets lower. Now if you want to remove any Unicode character, these are the Unicode characters. So you can remove it using this command x.encode. Only keep ASCII, remaining is ignored. So this is a command to remove the Unicode, because some emojis, if you want to remove it non-ASCII character, then this is a command to remove the non-ASCII character from the string. Okay, then I can also use NLTK. I mean, I will change Spacey or NLTK, whatever you want to do. So here NLTK downloader is there. So here all our NLTK packages are there, because NLTK contains so many things. If you want to quit the list or something like, then you write quit, or else you do X and cancel it out. Okay, so you quit. Okay, something like that. So if you want to remove a stop word from the corpus, this is a command. Okay, I failed to download stop words over here. So let me download the stop word. So here is basically a, so here is a stop word. This is a package stop word. So stop word package, you have to download if you want to remove the stop word from the a text. So this is the stop words. You have to use it over here. Fine. Now, if you want to remove the number, then you can remove it the number using, this command re. Just use a regular expression. Use this regular expression part, and you can remove it number like 3 and y. Okay, it will get removed. Oh, this cell is running actually. So I have to. Insert. So here is you can down. So here you just see it. You can remove the numbers from text. Okay, remove the mention. Now, if you work with the Twitter, then it is necessary to write the remove the mention over here. So it's very easy. Just write regular expression @s means some characters. So you can remove it using the corpus. So this DD News, Nitish Kumar, Arvind Kejriwal can be removed. Even you can remove the URL also. Okay. And you can, so here this URL is removed because it doesn't make any sense. URL. You can remove the hashtag also. The pattern is remain same. Has and hash plus. Okay. Fine. So this is after s left. This is get removed. Fine. Then remove punctuation. Okay. So this will remove you all the punctuation like mayor dot. Fine. And here it will remove the white space. Okay, this is white space, this is white space, because these are unnecessary token which needs to be removed. So these are the white spaces. So this is basically a text cleaning part. Okay, so we do all these things. Now you have an assignment actually. So the assignment is basically before I get into this next part, you have to do the assignment hands-on, and the assignment is download the HESOP English corpus from the following link. Okay, so this is a link actually. Paste over here. Okay, so you can take the English data set. Okay, download it. Okay. Yes. So download. Now I will tell you. One minute. Okay, so you just, I didn't share this file with you, but here I will tell you how to read zip file. Okay, so these are the command: unzip file, remove zip file. So this now what you are supposed to do is you have to add this file using this command. Oh, manage sessions. There are too many sessions. Okay, because I run so many, so I will terminate this one. I'll terminate this one. Terminate. So basically what I will do actually, okay, here you are supposed to, you have to create one notebook file. Okay, because it is connecting. See, you are connecting your to the Google instance. Okay, Now here you have to upload the file. The upload file means go to the download folder, English data set. So this file is get uploaded over here. Now you actually in stopword problem, I have to write these things nltk.stopword. So you can easily download it over here. I mean, you can easily do the text cleaning part. Okay. Anyway, let me show you over here. Okay. This none of this one text cleaning part. So in stopword part, you have to just add this one. NLTK, okay, NLTK stopwords. 1 minute. This is a library. I have to. So sometimes some issue comes and you have to deal with runtime. I mean, it's not some library issue. Okay. So America, like South Africa, now is a all get removes in different way of something like. So from this string, you have removed the stopwords. And this is a command to remove the stopwords. Okay. So let's back to over here. Now in this, what you are supposed to do, you have to upload the zip file. So once zip file is over, you have to unzip, you have to, okay. And then, these are the code. Now I am not going to share this code with you. I will give you after this lab. Okay. And what you are supposed to do is, you are supposed to do this 4 tasks. Converting all letter into lowercase, uppercase, removing number, removing punctuation, white space, and stopword. So whatever you have, I have already given to you. You have to do it in this IPython notebook. Now I don't share this file with you right now. So you start cleaning the corpus. Okay. So please do it.
Okay, sir.
Any doubt?
No, sir.
Asima, hello.
Yes.
Can you listen? Can you hear me?
Yes, sir.
So did you downloaded the file?
Yes, sir.
Okay, upload hua. I mean, did you uploaded the file in a collab?
Yes, sir. I'm uploading it. It's
Visiting
uploaded.
हो गया?
Yes.
Okay, okay. And then you see, you know what you are supposed to do it? You have to use pandas, okay, data frame to, you know, read CSV file. So in this, read the file and you will get the, you know, so first thing is data. I mean, you can use any give name and you can see the, what is the content.
So TSV file can also be opened with read CSV command.
Yeah.
Okay.
TSV is tab separated.
Okay, tab separated. Okay. That is comma separated. Okay.
And please, you can observe from delimiter is equal to.
Yeah, tab. Yeah, okay.
Okay.
Sir, Sandeep sir.
Yes, please.
Sir, Monali is here. Sir, do you post this assignment on classroom?
Yes. I have no. I have didn't provided the solution, ma'am.
No, I don't want solution, but the whatever you have just now shown us the file in which the different commands you have written. So that file you have given.
Yes. So if you go to the Google Classroom,
yeah,
get this document first. Lab 1 session on parsing.
1/6, sir.
Okay.
In classroom, where I can get this?
Yes. You see, go to the classroom.
Yeah.
Okay, 1 minute. Or let me. 1 minute. Okay. Just hold on. I mean. One minute. Huh?
Yes, sir.
Okay. So you go to the Google Classroom, you will get, I mean, you are supposed to download this file.
So I'm not able to view that file. Google Classroom.
Can I send you the link?
Yes, sir, please.
Okay. So just check WhatsApp, or I can even.
So you can share in chat or chat.
Okay, chat.
Sir, I am also not able to open that file. That's why it's better if you can share in chat only, in Zoom chat.
Okay, 1 minute. I will put this folder in the chat. So no problem. Don't worry. 1 minute. I'll share it. Because I have to cover, a lot of content today in a 1 hour, 1.5 hours. So I move very fast. I mean, it's a very trivial thing. It's not the, big deal. So I move really fast. I don't know whether I make some sense or not. Internet connection is not stable. 1 minute.
So because whatever I am getting under parsing, that is some zip file.
Yes, some rare file. So you first extract.
Yeah, but the PDF you have shown for assignment, it is there?
No, yes, it's a Word file. It's not a PDF file, ma'am.
Okay, it's Word file.
Yes,
So it
it's a
is
Word.
available.
Yeah, it's available. I mean, did you get the file? I uploaded in.
I share a link in chat. Please check.
Okay.
So Tanmoy dot rare file. You first the Bhargav, where did you share the link?
In chat.
Sir, it is asking you need access.
What?
You need to give access. Actually, it is showing access denied.
Now you can access that.
Which file?
Now you can access the file.
Okay, 1 minute. Hold on.
Okay, sir. Got it, sir.
Yes, sir, it is working.
Even in group I shared this file. So आप ग्रुप में देख लीजिएगा. ग्रुप में भी मैंने rare file डाल दिया है.
Yes, sir. Got it, sir. Thank you,
Now
sir.
see, the purpose you understand. That's all.
Yes,
And then
sir.
you have to finish the assignment.
Yes, sir. Yes, sir.
अभी tagging और ये सब बाकी है parsing. So please make it fast, because see, there is no point if I just run the cell. I mean, you have to do it because it's a hands-on session. So first thing is, you are supposed to download the data set, upload in a collab, unzip the data set, remove the zip file, and then read the TSV file. So how many of you have did this? I mean,
Sir, I have a doubt.
Done, sir.
Yes, please go ahead.
Sir, I was asking, I've downloaded the file from the link you have provided, but there is two file of .tsv. So which file I have to use with English underscore dataset .tsv? There is two file in the folder.
Okay. So you have to use one file, one English underscore dataset.tsv.
Okay, sir. Okay, sir. Thank you, sir.
Can you see my screen? I mean, it is written. I mean, just.
Yes, sir. I've just seen it.
Excuse me, sir.
Yes.
Actually, I have done up to converting it to lower, but I have confusion in doing the that is a punctuation, removing punctuation. Can you?
Punctuation. Okay.
Yeah. For string, you have given the example. For
okay, here data frame. So you have to run a loop actually. See what happened.
Okay. I have to take it as a
yes.
Okay.
If I will give you everything, then you will get done. Okay.
Yeah. Yeah. But I had the doubt whether
Just
I got
run the loop. Okay.
Thank you. And one more thing, I'm not in the group, WhatsApp group. Actually, I didn't Later on only I realized, will I be able to join in the group again? Because it was
Yes,
showing
yes.
explain.
Can you send me the email? I will share a link with you.
Yeah, okay.
Please. What's your name, ma'am? I forgot actually.
My name is Aruna Devi, sir.
Okay, so please. I guess I have sent you email to everybody to join the group.
Yeah.
To join.
Yes. Actually, I was about to join on that day, but I could not. I'm not able to join it.
Okay, no problem. Now let me ask you randomly, Leher, can you hear me?
Yeah.
Leher.
Yes, sir, I can hear you.
Where did you reach?
I have loaded the dataset and I've converted the text column to lowercase.
Okay. Very good. Now see, this is very good data set for hate detection. So I am giving you the data set which we offer competition across worldwide. So I am giving you a standard data set and you do the only pre-processing. Okay. Remaining thing we'll discuss later. So layer is done. Okay. Now let me ask to others. Srinidhi, can you hear me? Srinidhi? Oh. Srinidhi? Okay. I don't. Okay. Aditi, can you hear me? Aditi Dave. Aditi Dave.
Yes, sir.
Bhagwat. Am I okay? Aditi is there. Aditi,
Yes,
आप
sir.
कहाँ पहुँचे? Where did you reach? बताइए आप.
Sir, wait a sec.
Are you able to download the data set and upload it?
Yes, I'm able to download the data set, but actually I didn't have a RAR decompressor, so I had to download that. So I'm a little bit late on that part.
Please, because I have to check that where you have to follow. Okay. Then
Yeah. I'm able to follow it. I have done it previously, but it's just that I don't have the RAR decompressor, so that's why it takes time.
Ritika, can you hear me? Ritika Dhiman? Ritika, can you hear me?
Hello.
Yes, Ritika, can you hear me?
Yes, sir.
Okay, so where did you reach? I mean, are you able to download the data set and upload it in the college?
Yes, sir. I have downloaded and uploaded it. Actually, I was not able to access the file earlier, so now I've done it.
I have shared in a WhatsApp also, I guess.
No, sir. I can access it now. I was telling that why I was late a little bit.
No problem, please.
Yes, sir.
So these are the code actually. Translate, punctuation part, then removing the HTTP link, removing the lower. Okay, I'm showing you this code. Okay, so these are the functions. This is a function to calculate the length of tweet, punctuation count, SK. Okay, and here you will get the. So this is a final corpus for final corpus for process. So everything is in lowercase. We get the read of special characters. I will give you a time. Okay, in next 5 minutes, you to do it. Part of speech. Okay, so please do it in the next by tomorrow. Okay, corpus and your code file, IPython file. So these are tomorrow 12. So take your time. I'm Hello, can you hear me? Hello.
Yes, sir, we can hear you.
Okay, so what I will do actually, because since we are, 6:35, we are only 20 minutes we have. So what I'm trying to do is, let's finish the POS tagger, part of speech tag. Okay, I mean, you will submit the assignment by tomorrow. Okay, so there is no problem. I mean, so can we do that?
Okay, sir.
Okay.
Yes, sir.
Any
Yes,
any
sir. Yes,
any
sir.
query, I mean, any problem, what you are supposed to do is, see, you have to perform this task. Okay, first you are able to download the data set, then perform this 5 write down 5 function and share the code in a Google Classroom. Okay, along with corpus, process corpus and file.
Okay. Okay.
So shall we start the part of speech tagging? Fine. Okay. Okay. So I hope that you follow till now. Okay. So basically, in a part of speech tagging, there are 9 traditional word classes: noun, verb, adjective, preposition, adverb, article, injection, pronoun, and conjunction. So these are the 9 part of speech tag. Okay. Now you know that meaning, the semantics of the word depends upon the part of speech tag. Please remember, in a STEM, stemming and lemmatization part, in the meeting and we are meeting. Now here we are meeting and in the meeting. So the semantics of meeting is different because we are meeting. So here meeting is a verb and in the meeting means meeting is a noun. So the semantics are depends upon the part of speech tag. If part of speech tag is verb, semantic is different. If part of speech is tag is noun, the semantic is different. So that's why part of speech tag is very important. Okay, now some of the examples are, noun, we, adjective. So like chair, bandwidth, pacing, study, adjective, adverb, preposition, pronoun, and determiner. So these are the example of, noun, verb, adjective, adverb, prepositions, pronoun, and determiner. Okay, so please just go through this: the, that, those, determiner, pronoun, I, me, mine, prepositions, of, by, to, adverb, adjective. Okay. Okay. Now the process of assigning part of speech or lexical class marker to each word in a corpus. So if someone asks what is POS, then you are assigning part of speech tag to the each word in a corpus. What is the type of this? Fine. Like this, the will go to determiner. So tags and words. So this is part of speech tagging. We are going to perform these things. Okay, and application. Okay, like in a speech, lead or led by, we say lead, sometime we say led, something like object. So in a speech synthesis pronunciation, the part of speech takes place very important part. Okay, because the lead and led, when to speak led and when to speak leads, it's again depends upon the thing you can do in a spacey, or part of speech things you can do in a tagging also. NLTK. Okay, so in NLTK, let's start with the NLTK. So you have to import NLTK. Okay, word tokenize, download. This is a package, and average perceptron tag. This is things you need to download from NLTK. Okay. Now you just tokenize the text, and now for something completely different. Now these are the POS tag, part of speech tag. N means CC, coordinating conjunctions. Now Okay, RB or adverb. 4, in is a preposition. Then something, noun phrase, completely, adverb, different, adjective. So this is simple way to get the tag of the each word. Fine, it's very trivial thing. Here there is no rocket science. Okay, you have to just use it. You know how to use it. Now let me tell you. These are the syntax that we are going to use. Adjective, adj, add positions, adverb, conjunction, determiner, noun, numerical, particle, pronoun, okay, verb. So these are the example again. Okay, so you just go through over here. Okay, so this is very easy in a NLT. Okay, now let's move on to the spacey. I will teach you both. Okay, so you have a choice. So in spacey, you have to just use import spacey, and then we create the doc object. Okay, this is error manage session. So if you create so many sessions, then you have to terminate some of the session because Google won't allow to use so many notebooks. Okay, let me run. So part of speech tagging in spacey. Just hold on. Okay, so here you have to en.core, so you are using the English. Okay, my internet connection is unstable. Let me. Okay, so the quick brown fox jump over lazy dog's backs. Now this is the very good famous statement. Now we will try to create the POS tag. Now there are in spacey it provide coarse POS tag and fine grain POS tag. We will see, and spacey also give you explain tag. So description of the tag actually. So let's first try to print the text. Okay. Okay. Now, let's say the quick brown fox jumped. So this is a fifth word, jumped. Okay. Now, if you want to take the what is difference, then you will get the over here. So jumped is a fifth word. So here we write doc4.text verb. Okay. Text is a jump, position, then take VBD and explain past tense. So spacey.explain will give you the tag actually. So 1 2 3 4, 1 2 3 4. So this is the position of the word actually. So you will get the idea which one is better, spacey or NLTK. Okay, now these all are coarse grain part of speech tag, adjective, adverb, something like that. You just remember. We also discussed these things. Okay. Okay. Now, if you want to see entire document in the last sentence, okay, the quick, so determiner, DT determiner, token text, token position, token tag, and spacey explain. So 4 parts. So this is a stored word tag, DT, JJ, JJ. So adjective can be written as a JJ. Okay, and position is adjective. Okay, so these are the label which is used by tags, something like. Okay. I hope I am making sense. Hello.
Yes, sir. Yes, sir.
Yes, sir.
Yes, yes, yes.
Okay. Thank you. Okay. Okay, so these are the coarse grain part of speech tag. Now some of are, something like, a better, this JJ and JJR, JJS. So this is a superlative. So something like best. Okay. JJS, it is a superlative. Now this is comparative, JJR. So this is more fine grained take. Okay. So adjective, comparative, adjective, superlative, adjective. So here we are moving from coarse grain to coarse grain to fine grain. Okay. WH determiner, pronoun possessive. Okay. So based upon, I mean, these are the, I mean, just look at, I mean, it's doesn't any rocket science, just there are some, words. Okay. Okay. So similar example, working with POS take. This is all about the workplace. Even you can count now the part of speech taker. Now in a text classification problem or in some problem, we consider the feature that to count. Then this is the POS count. So what happens? I will tell you. This is a sentence. The big brown fox jump over the lazy dog's back. Now here we are counting the POS take. So 84, 85, 90. Now look at this. Here we will see attribute. Okay. So what is 84? 84 is a adjective. Okay. Similarly, what is 85? 85. Okay. ADP. Okay. Similarly, 90. So these are the basically, the IDs for the POS take. And you can create, something like, see, this is frequency list. Okay. So adjective, determiner, noun, part, punctuation, verb. So these are the frequency. Now you can consider this, feature as a, feature of the document or tweet or
Sir,
something like whatever
your voice is breaking a lot.
Put as a, feature in. Yes. Can you hear me?
No, sir, your voice is continuously breaking.
Can you hear me now? I have restarted my broadband.
Yes. Yes,
okay,
sir.
Okay. So sometimes, what happens. So basically, here, what POS count item. So we counted that the adjective are 3, ADP are 1, determiner, noun, punctuation, verb. So this feature can be used as a, that document contains 3 adjective, 2 determiner. So this is used as a text feature when we do the text classification or text clustering. Even you can do the fine grain. Okay, fine grain text, take count. So these are the fine grain, INJJ, DT, and BBD, something like that. Very trivial one. Okay, so this is all about spacing. Okay, so these are the fine grain. Okay, now this is very important. I mean, dependency parsing. What the professor, Professor Tanmoy was telling about, this is all dependency parsing. But I will keep to teach you this dependency parsing somewhere in, when we do the parsing, because the entire parsing is remaining. So whenever I will get time in the next 8 days, I will teach you parsing and dependency parsing. So till now, I mean, let's finish the session over here. Any question? Hello.
Sir, do we have any assignment on this POS?
No POS.
Okay, sir.
Oh,
So today we have only
okay.
one assignment, whatever previously you have said.
Okay, and second assignment, I will give you verbally that you are supposed to write down a Python script, one line part Python script to capture email address from the text. Can you, I mean, this is a you know, assignment on regular expression. Okay. Hello.
Yes, sir. We got it.
What?
Yes, sir.
It is one line Python script to capture or to, you know, capture email address from the string or whatever you like. Okay. So this is second assignment. Fine. And for parsing, I will teach you, you know, somewhere because there are still 8 days, 7 days are, you know, left. We'll do it something. Okay. Somewhere parsing. I mean, I have prepared, I have shared file with you also. This is a parsing notebook, but the time is over, so I will little, I mean, it's very simple, you can just check it, probability parsing and something like that. Okay, so thank you so much. Any question once again?
Thank you, sir.
Okay.
No,
Thank
sir.
you, sir.
Thank you, sir.
Thank you, sir. No questions.
So you can leave now. Thank you. So we see you tomorrow at 3 p.m.
Yes, sir. Okay.
Yes, sir.
Thank you, sir.
Okay, thank you.
So the regular expression assignment is not for tomorrow, no? The email.
I mean, you can, I will ask you, okay, just you to write one Python script actually, one line.
Okay.
Okay. It's not assignment, it is just question, I mean.
Okay.
Okay. Okay.
Submit.
Yes, capture the, you know, email address from the text. It can be string, it can be document, anything. Okay.
Okay. So the current assignment is what all?
This one.
Okay.
For text. Oh, this is assignment. Now the supplementary assignment is one Python script, simple. Okay.
Okay. Okay. Okay. Thank you.
I
Sir.
didn't mention it. Okay, thank you. I hope you have understand. Okay. Now let me ask to Aditi. Any question?
No, sir.
Sandeep, so there is a question in the chat box, like from where that data set is downloaded in post.ipynb file.
Okay, POS IP. Okay, let me tell you. This is Spacey. No, I have not downloaded any data set for, you know, POS. That you have to just load this Spacey parser. I mean, Tiger. I mean, no data set in a POS. I mean, we are not using any data set. We are just using some string, quick brown fox, something like that. Okay. Okay. So, Kavita. This question asked by Kavita. I hope that's Kavita Patil. Okay. I did not use any data set for the POS taking. Okay. Thank you. Any more questions?
If there are no more questions, then I'm ending the meeting.
Okay. Yes. One new message. Okay. Please.
Okay.